even ones that were big in our news scene, like the British Airways breach, is only a tiny blob on here, and they're absolutely happening all of the time. And all of these breaches will involve personal information about you and your life, and most of them tend to involve passwords, either passwords that are completely unencrypted or passwords that are easily attackable, as we saw on the last stage. And if you're thinking, well, it doesn't matter if the occasional hacker in a basement somewhere gets hold of my passwords, there's only a few of them in the basement, what harm can they do? Well, the sad truth is that there is a massive sharing economy when it comes to stolen passwords. And it gets shared on the internet and the dark web routinely. And of course, if it's on the internet, someone is going to index it for you. And so companies like this exist. This is from Securio, where you can go and look up how much trouble you're in. This is all the Dave Palmers in the world who have lost, well, it's not by any stretch all of them, some of the Dave Palmers in the world who have lost accounts and passwords. I am in this list on that screen. And unfortunately, there are an awful lot of these going around. It's completely commodity now to look someone up and gain access to their passwords. And these passwords are pretty dreadful. These are all passwords from Dave Palmers around the world, including me. I'm not going to tell you which one's mine. And as you look at this list, you can see they're pretty awful, aren't they? Hannah, Palmer 12, well done. Palmer 9, Palmer 1. Turns out Dave Palmers are pretty bad at setting their passwords. If you're looking at number 63 and you think, this looks like a great password, well, it turns out that's just a different computer representation of Jackson 5 that is also in the list. And someone's charted out their entire relationship status. Dave somewhere in the world has been with Kathy, and then on the plus side, at least it got longer. So these aren't great. And why am I talking about this at an AI conference? Well, there are 1.4 trillion passwords and personally identified information, all in structured data fields that just Securio, who are the company that provided that service we saw on the last slide, have seen on their own. So ignoring everyone else that's collecting up passwords that the bad guys are sharing around, one company has got more than 1.4 trillion structured records, and we can see these come in clumps. There are sports cars, there are partners' names, there are sports teams. There are clearly cultural norms and clusters in the way that Dave Palmers around the world set their password. And this is a representative set. I haven't fiddled with this to make it look worse than it is. All I've done is try and take duplication out of this list. And all of you who are interested in AI, this is not being thought about really in the security community, but in the AI community, you will recognize this is an amazing training set to start creating systems where from an email address or even just from someone's name, you would be able to start creating predictions about the likely passwords that they have. And now you don't have to search 5.8 quadrillion different records to see if that password is your target. You can probably interact with a relatively simple to build system and have it give you a list of the passwords that likely exist. So I think there's a storm brewing there. And if you're thinking, hey, am I clicking this wrong? Thanks. If you're thinking, well, you know, I work in innovation, or I'm a thought leader, or something like that, why does it matter? I haven't got any data worth stealing in my organization. Well, this is an example of a criminal getting a foothold in just one laptop, and within less than 59 seconds, that laptop has been used as a bridge to infect every other computer in the entire organization. And this is an agricultural firm. We go from one laptop to everybody else's laptops, a bunch of servers, and even through to the manufacturing floor. 59 seconds, way faster than human beings can expect to react. And this is a mid-sized firm here in the UK, but it happens to mass-scale firms as well. If you're familiar with Maersk and some of the stories of trouble that they had the year before last, They lost 45,000 laptops and 4,000 servers, absolutely everything in their digital business, in the 14 minutes it took their head of security, Andy, to go from a meeting back to the office. 14 minutes, game over, no more Maersk, back to pen and paper. And the point here is criminals don't sneak around anymore. They kick the door in and they go wild. But what we have here is a systemic weakness that is identical across the whole of the business. There's no AI in that attack or the Maersk one. But what we should reasonably expect is AI modules to get put into these self-spreading worms where they treat their activity of spreading around the network like a game of chess. What is the maximum control I can exert in a single move? How can I strategically outpace the defenders and what they're trying to achieve? And how do I trade off detectability versus speed versus impact? This notion of overwhelming human defenders before they can react is amazingly successful, but you will need smarter systems as defenses keep improving. Consumers are suffering differently, but also in kind of similar ways. If someone gets into your email because they've got a bad password, I've been helping a young lady recently who someone got access to email. They immediately reset the password on her mobile phone provider. Once they got access to the mobile phone provider account, they ported her mobile phone number to a handset in the criminal's control and then went nuts. They took her Uber Eats account, her Amazon account, her Airbnb account, John Lewis account, strangely. I wouldn't have thought you could conduct much crime with a John Lewis account, but there you go. And then finally, to make sure her life was a total digital misery, they took all of the money out of her NatWest bank account and then went after and reset her Apple account as well. Where do you begin when you've lost every piece of digital identity in your life? You don't have your bank account anymore, your mobile phone number, or your email account. You are pretty stuffed. Now, this is happening at the moment with human beings, but it takes about an hour, and you have to pay those human beings. So it's absolutely certain to me that we will see semantic processing being used for AI systems doing this. Within a minute or two of gaining access to someone's email account because you've guessed their password or found it, then game over for that account. Obviously a lot better if you've got two-factor authentication, but that only gets you so far. I am enormously running out of time, so I'll cover a couple of things very briefly. Even if your passwords are great, other people in your life will become a vulnerability. Azeem and I have been emailing each other about this event today. We can reasonably expect systems, instead of involving human beings faking emails from Azeem's inbox, that if someone gets onto Azeem's laptop, an AI system could automatically recognize we have a shared diary appointment, we have some shared communications, and shoot me an email that sounds like Azeem, that's roughly his communication style, and is contextual enough that I will just click on it. So these are the things that are, to me, relatively obvious evolutions of what AI is going to bring into the environment. I think we will see these in the near future because they make criminal activities much more profitable per victim. They allow you to hit a lot more victims at once. And crucially, the less human beings you've got in your criminal enterprise, the less likely that the FBI is going to flip one of them and get them to snitch on you, or someone does something stupid that it means that you get caught. With that, thank you very much. I'm going to just skip through the rest of these.
Fantastic. That scares me so much. I was actually emailing my wife to do something password related because actually I'm terrified down to my socks. Now what I'd like to do is bring up to the stage Robert Hercock of BT to tell us about what he and the organization is doing beyond telecoms. Go for it, Robert. Thanks.
Right. Are you all awake? Are you happy? You won't be soon, don't worry. Right, so that's me. I like to go back in time a little bit. So people think of AI and cyber as very new processes. In actual fact, this all began literally back in the 1940s. So we've just had the D-Day sort of anniversary. This is Colossus Mark II, so state of the art. I know it looks primitive, but really state of the art. This is what's interesting. Cybersecurity and AI and computing all began at the same time, the same genesis point. Turing, in this case, Tommy Flowers designed this machine. We're all working on the same set of problems. And the two fields then kind of diverged. So cyber went one way, with the encryption piece. AI and its sort of evolution went another way. We're now seeing these two fields come back again. This is what matters. My takeaway for the day is people think of security and AI as different domains. Now they're not. They're both sort of on a parallel track and increasingly going to intersect with each other. So the good news is, people think of BT as a broadband provider. We are also a global network player, and we have about 3,000 people globally working on cybersecurity. And it's a 24/7 job, as Dave was just saying, to protect everyone. The bad guys don't sleep. They drink a lot of Red Bull. So it's a 24-hour problem. And also, it's massively increasing. It scares me how fast it's increasing. Okay? Hundreds of thousands of new malware samples, millions of malicious new email attacks per month. You can read the numbers. It's huge. And that's another key point. So in my research team, we're looking at how we can use AI and machine learning to defend networks, to defend everyone. Because we have to automate the process to a degree. I'll also come on to how far you want to automate that process. That's another question. Similarly, this is a quick slide deck of where we are. So one of the biggest ISPs, global enterprise. I said over 3,000 people just in security, just in cybersecurity. Terabytes of data per second. I don't know about you. I can't read a terabyte a second. It just blurs. It's very hard. So what are the risks that we're facing? We're facing every kind of risk. So hacktivism, moderate level risk. People get annoyed with some major companies, some animal rights process, whatever it is. Criminal risk high, as Dave was just saying. This is big business. This is professional business. You can go online to the dark web. You can pay $10, get a DDoS attack on somebody you don't like. Please, don't do that. Terrorism risk, that's an interesting one. Risk actually moderate. That's interesting because people you think of as being very malicious, for them the cyber domain is a tool. It's a recruitment agency. It's a money laundering process. But it's not for them. It's not core business. Whereas for the criminals, it's core business. It's how you make a living. It's a different. So intent matters in terms of the threat level. Nation-state risks now very high. So most nation-states use cyber increasingly as a influencing process, as a political process, as a way of shaping other countries' activity with you. Increasingly, we're seeing that. And insider threat, of course. Insider threat is a complicated one. The risk can be very high, and it depends which conference you go to as to how frequently you think that happens. Dave mentioned Maersk, the shipping company. So one of the biggest attacks a couple of years ago, 2017, was NotPetya. So this was an attack. Basically, Russia attacked the Ukraine using a cyber weapon they stolen from America. And many companies got hit for hundreds of millions of dollars. The total cost was about $10 billion. This was not small change. The interesting one was Maersk, the shipping company, for this reason. It had a huge impact on the physical world. This was not bits and bytes. Thousands of container ships were stuck in ports because they couldn't unload. The computers that would control the unloading process had no data. They didn't know where the container's supposed to go. You can't unload this if you don't know where the container's supposed to go. Yeah? And so you had ships backed up. You had convoys of lorries backed up into ports. Maersk controlled something like a third of the world's shipping. This has a huge critical infrastructure impact. So it's just to sort of embed that losing your digital identity in your phone is annoying. Not being able to supply your country with resources is very annoying. So what are we doing about it? So I lead a research team in BT where basically we're trying to combine AI and visualization, data analytics. So we do a lot of visualization of the data. So personally, I'm a big believer in that human beings are not so great at calculus, usually, but we are very good at visual processing. The thing inside your head evolved to be a visual processing system. That's what it evolved to be. You are all superb at color recognition, pattern recognition. You can see the texture of this building. You are brilliant visual engineering systems. Okay? So let's translate the data into something the human being can process. So the point of this tool is that to give our security analysts a way of hoovering up the data. That we use the AI to classify everything. That's what these colored blobs are here, where the AI is trying to classify, categorize all the massive flows of data, gigabytes of data per second, and give the analyst, because you only ever have a small number of analysts. You never have enough security analysts. If you want a job, by the way, see me afterwards, if you have any skills. And this is a more boring technical deck, but it just illustrates that we're using a whole full range of AI machine learning tools. In this case, deep learning. So for many years, we've used standard machine learning, statistical methods, Bayesian methods, things like that, like spam filtering. Increasingly now, we're looking at things like vector embedding, convolutional neural networks, reinforcement learning. In this case, to identify botnet attacks, the little colored squares where the tool's learning. This activity in the network looks odd. Yes, you can get false positives. Yeah, no, it's not perfect. It's a continuous research process, and we try and push our research outputs into the business. Go to the next slide, Dave. Then another tool we've been working on is something called Nexus. So a nice thing is that you can apply graph theory to a lot of data processes. So you can think of like whether it's a social graph, an IP network, a supply network. A lot of data systems can be modeled as a set of nodes and edges. And then you can actually apply quite sophisticated visualization tools. And we've built this in-house. This is our own tool. We've developed it in our research team. And just lets the analysts explore large-scale data sets. It makes pretty pictures as well, which is nice. What was useful about this, we designed this tool originally to do both supply chain and IP traffic, when we thought, just a minute, this is identifying a botnet in the system. This is a general purpose graph engine, so you can actually apply it to a wide range of applications. And one of the ones that relates to the massive increase in ransomware activity going on at the moment is Bitcoin. So this is actually Bitcoin data. This is transactions in the blockchain underlying Bitcoin. So the preferred criminal payment method is Bitcoin. So if you hack someone, you do ransomware, you want Bitcoin payments. So in that case, we're drilling into exploring the Bitcoin payments graph. And in this case, these sort of three blobs down here are the malicious wallets from the WannaCry attack. So when WannaCry hit 2 years ago, those are the actual wallets in that Bitcoin network where the criminals were taking payments. Interestingly, there's about $300,000 sat in those wallets. Don't try and access it. It's not a good idea. But this tool like this lets you explore and interact with this big data set. And this is another point. So cybersecurity increasingly is a big data problem. You're looking for a weak signal in a vast amount of data. So it's how can you accelerate that process and help the the analyst or whoever your engineers are fix the problem. We're also called the craning group, whereby the other people in our labs were quite jealous of our coloring skills. Right. Going towards my sort of summary, I think this is the key point. As Dave was saying, we're not really seeing the bad guys using advanced AI yet. That's not happening. I think it's going to happen. Excuse the audio hacking going on at the moment. So I think within the next 2-3 years, we will see AI and especially deep fakes, the whole deep fake process being used for malicious purposes. In this case, identity. We're going to see AI itself become more diverse, become more heterogeneous. It will start to mirror the cultures and societies that are generating it. We won't just have a vanilla AI. There'll be a global variety of different kinds of AI with different norms, different behaviors, different attitudes, different responses to how it interacts with human beings. And all of those will be used for malicious purposes. And then this is the point we're going to get to. Who's behind the mask? Is there anybody behind the mask? When you're dealing with something online or something's doing an interaction with you, how will you know what it is that you're dealing with? Is it human, a mix of human and machines, or just a machine? And that's critical for security because identity is the crux of security. You can't have security without identity. Who is this actor? Does this actor have the right to do the thing they want to do? I don't see an easy solution to this. This is very much a research problem. identifying and stopping deep fakes, deep videos that are being used for malicious purposes is going to be a horrendous problem. And even more so when it's text, like the OpenAI tool that was discussed recently. How do you detect when an email coming in is a spear phishing email? And these days, there's always some kind of giveaway, some clue that it's not what it's supposed to be. And if you're awake and you've had lots of coffee, you spot it. However, when that email's been crafted by an AI in a very refined way, knowing everything about you, it will be a horrendous problem. That's something we're going to have to face. So, conscious of time. So deep learning is fantastic, great tool, amazing tool, but it's going to accelerate both defensive and offensive cybersecurity processes. So we are using it for defense. That's fantastic. It accelerates our ability of the analyst to go through large amounts of data. But the bad guys are going to wake up quite soon to the potential of it. And for them, it's just a business process like anything else. Then we get into sort of a cultural dialogue about, what's malicious. Depends who you are. The next question that usually comes up in conferences is, how autonomous should the defending AI be? Because the question says, Robert, can't you just take the humans out the loop? If you watch war games, let's take the humans out the loop. We'll just automate the whole process. You can do that, but please don't. Because the first thing the bad guys will do is say, aha, you have a fully automated AI defense system. I will now spoof you and force that AI to overreact and cause an autoimmune disease whereby you shut down your own system. The first thing the bad guy's going to do, well, the first thing I'd do, if I was attacking somebody. Ken made the mistake of saying there are 3 good guys turning up today. There are 2 good guys. They're over there. Actually, there's a caveat on that one even. I think within 5 years, you'll get to the point where you can't have the human in the loop. As Dave was saying, the speed and volume could rapidly get to the point where you have to fully automate. And that's going to be a fascinating world in which the AI is defending against attacking AI. Make sure you have a very long password, okay? You want like a 40-character password. Right. And the final point is explainable AI. Current deep learning systems tend to be very much black boxes, very hard to inference why they reached a decision. And if in the security domain, that's no good. You need to know why something was done. Why was a decision taken? You need to be able to trust that decision. And this is very much an open research question in the security community. How are we going to get a more transparent inferencing mechanism that we can rely on and explain to the stakeholders, business community, this is why the defending system took this decision. And on that decision to shut down a particular subnetwork was a valid decision and wasn't something that was being spoofed or maliciously driven. Okay? Are you still happy? But you're not worried enough then. Okay, next up, right, yep. Okay, thanks a lot, Ken.
Hey. Thank you very much. Okay, so who here, that's a great question to end on. Who here is happy? Raise your hand. Have you not been listening? Who here is terrified? Raise your hand. Raise 2 if you're really scared. Come on. Like, I'm literally telling my wife, change the passwords. Okay. Grace Casey of Cylon. Take it away. Thanks a lot.
Thanks. Hi, everybody. Good morning. So very briefly on Cylon, we are a startup program that finds, grows, and invests in some of the world's most exciting emerging startups in this space. And we've been doing this for just over 4 years. And in that time, we've assessed about 1,000 applications from startups across a whole range of this very diverse field. And as you can see, about just under 10% of those applicants have actually made the cut to join our programs in London and Singapore. And rather than kind of add to the level of depression here today, I thought what I might do is try to talk a little bit about some of the themes we've seen emerging from the innovators that we work with, and give you a bit of hope that there are people working on some really interesting solutions to some of the issues that Dave and Robert have identified. So from those 1,000 applications, obviously there's a huge number of themes that one could pick out, but given that I have less than 10 minutes, I'm just going to pick out a few indicative areas. And the first of those that I would dwell on is the continuing importance, the prevalence of human factors in cybersecurity. And that manifests itself in two key ways: fallibility and focus. So first, fallibility. Still the case that humans are really responsible for the majority of breaches that we see happening now. In fact, I think research shows about 88% of all breaches originate from a human problem. Much of this is really basic stuff, as David said, having poor passwords in the first place, reusing those passwords, misaddressing your emails, and then perhaps earlier on in the process, developers writing code that contains mistakes and then gets built into a product and lies dormant until a criminal can find and exploit it. And then there's phishing. And evolution has made us all surprisingly susceptible to a well-judged cat video. And that's before you even get to some of the more AI-powered, more sophisticated targeted attacks that Dave and Robert are talking about. The really basic stuff still gets us. And any amount of awareness training, which is still the industry's default response to this, doesn't tend to stop people clicking on these links. Because it's pretty cute. Who doesn't want to click on that? So in a way, cybercriminals are really attacking human nature. But the scale and the rapid evolution of this problem also presents us with a massive opportunity, and we see some really interesting new approaches being developed and applied by startups that recognize that the answer here is not better and better firewalls, but it's trying to reduce the amount of human error in the first place, and often that's with a judicious application of AI. Some examples in that space might be the use of machine learning to reduce the scope for user error. An example there might be a company like Tessian that's applying AI to stop you sending emails to the wrong people by accident. Other examples are the application of psychology and behavioral economics to try to instill better security practice inside organizations. And much of that builds on nudge theory and the other work of people like the Nobel laureate Richard Thaler. And there's a number of really interesting companies in that space, like Immersive Labs, Outthink, Boser on Security, that are all trying to create a different way of addressing this challenge of awareness and training. Or it might be through creating better code in the first place, and there's numerous companies trying to help developers to build security in as they're developing their products in the first place, and also to check the open source components that many people are using to build their products without realizing that they already contain vulnerabilities. Now, this problem is not going to go away because we are human, after all, but we do start to see some real progress among innovators working on this human problem. The second area which I'd mention in terms of human issues is focus and the difficulty in finding it. Many people who work in the hard end of information security will tell you that their jobs feel a bit like this. They're walking into a pretty stiff headwind. There's too many threats, too many alerts, too many products, and not enough skilled people to help them prioritize and respond to incidents. And as we've heard, adversaries are getting better and more sophisticated all the time. One response to that is to throw more resource at the problem. You can try to hire more security people. You can even outsource your problems to a managed services provider. But the reality is that skilled security professionals are extremely hard to find, and managed security services are very expensive. So realistically, those are not solutions for most companies out there. And we see a lot of innovators helping to provide some focus in this challenging circumstance. And AI and automation is absolutely part of that response. See a huge number of startups around the world thinking of how to apply automation, AI, machine learning to aspects of this challenge of overload. From gathering and disseminating threat intelligence, to monitoring a complex and highly permeable membrane around an organization, to actually managing and responding to incidents. In all those cases, automation and AI can really help to distinguish signal from noise, allowing your highly skilled people to spend more time focusing on what really matters. Dave's company, Darktrace, is really in many ways the granddaddy of this approach in security, and there's any number of other examples of the trend towards automation and AI and security. Newcomers like SocView and Sensient from our Cylon portfolio to bigger, more established players like Demisto, which, just to illustrate this trend, was just bought a couple of weeks ago by Palo Alto Networks for $500 million. What else do we see? Well, an awful lot, actually. Just to underline, especially for any of you who are less familiar with this world of cybersecurity, it's a massive topic with almost limitless array of angles to it. So I'm just going to pick out two themes which are somewhat less headline-grabbing than some of the things that we've heard about already today, but I think nonetheless are fascinating signs of shifts in the way people are thinking about protecting themselves. First of those is supply chain risk. This has shot to prominence in the last year as an increasing number of breaches, probably 60% or more, are shown to derive from third or fourth party risk. Techniques for managing this have traditionally been really manual, sending out surveys, managing spreadsheets, hiring an audit firm to help you manage it. But typically, you're just getting a snapshot, and you can't actually keep up with the pace of interconnectedness between companies or the range and pace of technological change. But the good news is that we see some really great companies emerging, which are applying techniques not dissimilar to the social networks to increase the visibility of suppliers and their contingent risks. And that's companies like CyberGRX, RiskLedger, and Interos, all of whom are really bringing this new, more sophisticated approach to mapping supply chain and risk. And if that wasn't already less exciting to you than nation-state threats and AI bots, I'm going to mention insurance. So do stay awake for this, because it's actually quite interesting. The evolution of cyber insurance is a real theme that we've observed in working with startups over the last couple of years. I think this is a result of people and companies accepting that you can no longer create a perfect defense. When it first appeared, cyber insurance was very much about transferring a risk, perhaps providing some financial security around physical assets. And frankly, it was, and still to some extent is, very challenging to price a cyber risk. But as insurers are spending more time working with innovators who are deploying these more sophisticated approaches we've heard about, cyber insurance now looks increasingly like an essential part of a risk management approach. So many policies will now offer you access to experienced incident management services, and many will actually focus on building resilience into your business practice in the first place, clearly to help you try to avoid the problem and to manage it better when it probably inevitably does happen to hit you. This kind of thing, I think, is particularly important for SMEs who have more fragile balance sheets and can't take advantage of some of the very sophisticated tools and expensive services that are out there. And finally, how does all of this translate into what we see people, users, and investors actually spending their money on? Well, there isn't much data out there about what ordinary citizens are using and spending money on in terms of security products. I think antivirus is pretty well used, well understood these days. But beyond that, my guess is that most people outside of the tech world are not yet using the next level of protection like a password manager or using a VPN to access the internet. So my personal plea to you today, on top of Dave's request to you to extend your passwords, is also to use a password manager. If you're not using one already, they're very simple and they make a big difference. Within the enterprise, there's obviously much more data available. The picture is constantly changing, and as Forrester Research in fact describes it, chaos is the new normal. But even if it is chaotic, you can discern that security budgets are high, and in most cases are rising, with major areas of spend around cloud infrastructure, threat intelligence, and human risk. And interest in these innovative new approaches is underscored by what we've seen in the first 2 quarters of this year, which is a huge surge in cyber M&A activity. I already mentioned Demisto. We've seen a whole batch of big money acquisitions happening in this space in the last 3 months. Companies like Recorded Future, Webroot, Meta Networks getting acquired often at big multiples on their earnings. Back at the startup end of the spectrum, we're seeing an increasingly active VC community here in Europe, and Europe absolutely is now starting to be seen as a leader in this space. Sequoia's investment recently in Tessian Series B is a great example of this trend. That's a very brief rush through. Look forward to discussing in more detail in the panel.
Thanks, Grace. That's great. Grace, stay on stage. Join me in one of the 3 chairs over here. Let me bring Robert and Dave onto stage as well. What I'd like to do is have a very quick set of questions with them, a lightning round, so I can allow you guys to ask questions. But first, I want a show of hands. Who here is more scared after you've seen the presentations than you were when you walked in? Raise your hand if you're more scared. Okay, so that looks like 21.3% of you. Who here is less scared now that you've seen the presentations? Here's a little bit more relieved. So yeah, 2 people, 3 people, optimists. Okay, I just want to point out that these guys were talking about solutions, and you're more scared. Okay, let's just go with it. All right, guys. I want to get a sort of a yes or no, a one-word answer from you from the questions that I have right now. We're going to start with you, Grace. Are we winning the war or losing the war?
Winning.
Stalemate.
Losing.
This is great. What a great spread. And you're like the deviant stalemate. Okay. So why winning?
Look, I'm not going to pretend that this is easy. Far from it. That's been made pretty clear today. But what we're doing is working with the really smart people who are trying to build the innovations to tackle this. And I think if you spend time with those people day in, day out, you can't help but be quite optimistic about the chance that we are winning this war and can continue to win it, even as criminals start to adopt some of the methodologies that Robert and Dave were both talking about. But I think we wouldn't be doing what we're doing if we didn't see some really smart solutions emerging.
Okay, Robert, does that convince you? Are you wrong?
Deep down, I'm optimistic, in the long term. But an interesting story is, that when the police ask a bank robber, "Why do you rob banks?" He says, "That's where the money is." It's the same with digital. Why does cybercrime happen? That's where the money is. We had moved into a cyber world. That's where all the resources, the assets, the money is. So the incentive for criminal activity is huge. And so fighting that is just going to be an ongoing battle.
Okay. Dave, are you, you're sort of hopelessly divided.
I think we're getting better at responding to yesterday's problem, but our digital organizations are exploding in complexity. We are way past the point of human comprehension where you can get your head around everything that happens inside of an organization, how people work, what's happening with all those different systems and data. Yet we still ask, hey, Bob, you're the head of security, go and just find out everything that happens in Maersk and make sure it's secure. That's
all right.
Not really.
Okay, I'm going to now ask the audience. You can't say stalemate, and the reason why is that, although it might be a stalemate, there's a little bit too much blurred in the center, a little bit more of the Gaussian distribution, too much of the mean. So let's sharpen this, crystallize the issue. Are we winning or losing? All those who say, hey, all things considered, we're winning the war on this. Tension's being paid, products are being built, it's happening. Raise your hand if we're winning the war.
You said you were winning.
Okay, that's not a lot. That's like sub 10%. Who here says losing the war? Oh my God, we're losing the war. Okay, who here is still on a BlackBerry who's not voting? Like that guy over there. Okay, nudge him. Winning or losing? All right, we're going to go right into questions with the audience because you guys came here. You have a lot to think about and say and a lot to contribute as well. It doesn't have to be a question. It could also be an observation. But whether it's a question or an observation, it has to be short because we have 10 minutes. So go for it. We have a mic in the audience. Why don't I saw your hand first, then yours. Great.
Hi, my name is Patrick.
I just sit down. Oh, it's being recorded.
Very short question to all of you. Europe is betting on explainable AI. How can you do explainable AI when you have such complex systems where things have to be automated eventually and AI itself has to be autonomous?
Great. The chimera of explainable AI. Robert, you said we needed it.
I'm optimistic. I mean, interestingly, so if you look at the deep learning world that we have now, that was the technique invented back in 1992-93, Jeff Hinton and co. There were many of the AI algorithms being developed in the 1990s, evolutionary computing software agents, that have great potential. And the software agents in particular can be a much more transparent process. And I think we're going to see a resurgence of the whole software agent concept in AI. especially in security, has immense application for security, and inherently that's a more transparent process.
But the underlying his question is the idea that if we know something works, offers better protection, but we can't explain why it works, why should we bother with explainability? We got the benefit of the improved performance.
Yeah, I mean, trust me. If it works, I'll take it. Yeah, and I'll worry about how explainable it is. It just that's a nice. Just it's easier to get the investment from your executives, your stakeholders, if you can give the explanation of why things are going on.
Okay, there's a question right here. Wait for the mic.
Hi, thanks. The question is to you.
He's nice as well.
Of course. But you mentioned that in probably 5 years, it would be impossible to have a human in the loop. It's something that scares me, and I was wondering if you could expand on this and maybe explain what the role of cybersecurity experts would be in that scenario.
Yeah. I think what we're beginning to see and what we're applying is the best world is a hybrid mix where you combine the best of the machine and the best of the human. And that, I think, will be the way forward. It's like the best chess systems are often combined hybrid human-machine players. So human beings are still great at contextual knowledge, sort of social reasoning, the wider awareness. So the idea is to lift the floor of, you don't have your analysts doing the lower level stuff, you move them up to higher levels. So they're reasoning about the consequences and the sort of meta aspects of the problem. And you have the machine increasingly automate everything else underneath. I do worry that you'll get to the point where even that's not possible, in about that 5-year time frame where the AI is also doing sophisticated reasoning about your counteractions against it, and then you have to fully automate it, and that'd be really interesting.
Dave and Grace, let you come in on this as well. Humans in the loop, yes or no?
I agree with Robert. I think they will set a strategic tone or risk balance, but the machines will enforce it. So a human security person should say, I don't want unexpected data loss from the organization for any reason. If it's unexpected, stop it. But the myriad of ways that will be enforced in your cloud, in your SaaS systems, on your laptops, mobile phones, that'll be AI reasoning and decision making, and will be essential to mitigate the speed of attacks that we saw on the slides.
Yeah, I think the same applies also to humans. I think will still be determining the risk management of the organization. What are the most important assets to you? Is it your physical assets? Is it something else? Is it your reputation? I think it's still going to be humans that set that strategic vision. Right. But as you say, it's going to be enforced by machines increasingly.
Great.
An observation which I can like to comment on. Rather than a technical issue, if we look at this as an economic issue, surely why we're winning is because we've woken up to the tolerable risk economically of what this means to us. Cyber's always been at security a Cinderella to service delivery, but surely that's no longer the case.
Great. Let me do this. There's a lot of people who have their hands up, and I want to give everyone a chance to give like a 30-second question or intervention, and then ask the panel to summarize and choose one of those questions. So I see a woman back there. We'll start there, and then we'll work our way from the back of the room forward. Yeah, so the person right straight ahead to the left, to your left, waving furiously.
Thank you. So in the midterm, I think it looks quite clear that it will be a sort of mass identity fraud for normal individuals. Might be positive in the long term. And I think that a lot of normal people still have some kind of illusion that police force will be able to help you out, which clearly isn't the case. So I'm wondering, for all these people that will be exposed to these kind of things in the midterm, are we looking at a privatized law and order, and will the technology to help be democratized enough to support normal sort of low, mid-income people?
Great question. There's a gentleman right behind you, right there.
What do you think quantum computing will introduce into cyber security and threats?
Great, good question. Gentleman right there.
Just like explosives and guns were essentially developed as technologies by governments or for governments, the majority of the tools, certainly that I'm aware of, are for hacking, theft, cyber criminality were developed by government organizations, whether in the West or not. So as long as governments, how can we stop governments essentially developing the very tools that get put in the hands of criminals,
Sure.
which create these problems?
Great. Gentleman right there. Oh, no, he's passed. Same question. And then there's a woman there. Great.
Hi. You mentioned something about identity being very critical to security. Yeah, I'm just really concerned about what happens if I lose control of my identity. How do I re-establish this? What's the technology? What are the companies that are working in this to secure so that I can take back my identity? How do I prove that I'm myself?
Great. Identity. There's a gentleman there, please.
Hi there. It strikes me that this is one of those areas in which data about what's happened in the past isn't that useful to determine what you should do in the future. So attack vectors that have kind of previously been used don't necessarily give you an idea of what might happen in the future. So somebody mentioned using password managers. It strikes me that using password managers is a good idea until it isn't.
Yeah.
I wonder if you comment on that.
Okay, at this point I'm going to give it back to the panelists unless someone has a really urgent question that we've not raised that we should all have on our radar screen. Nope, great. So, Grace, why don't we start with you? If you can choose one of the questions, this is a summation, you've got basically 60 seconds.
Yeah.
You can ignore all the questions and simply riff it, but please.
So I think the lady's question was around, remind me, it was
privatization.
Privatization, yeah. And I think it's a really interesting observation, interesting challenge. I think as we see more and more individuals and businesses migrating all of their data and assets to the cloud, increasingly we're going to see a small number of cloud providers essentially becoming your personal security force. So if you have asked AWS or Google or whoever to manage your data, you are essentially putting your trust in them to preserve your identity, your personal assets and data, whether you're an individual or a company. I think that's a very, very interesting thing for us all to think about. I think it does present some ethical challenges. I think it sort of links in a sense to your question around your identity, which I think you're right to be concerned about that. We see in other areas of technology this great trend towards sharing and not owning assets anymore, car sharing, home sharing and so forth, and increasingly people thinking you don't necessarily need to own physical assets in the same way. My hope is that the counter to that is around your personal data, where people start to feel more concerned about owning and controlling their personal data and assets. And quite how that fits with this migration to large cloud providers owning a lot of it, I think there's going to be some tension there, but I think people do need to start to think about this need to not have an assumption of sharing your personal data.
Great, thanks. Robert, let me ask you, in 60 seconds, can you choose one lasting?
I'll go a different direction entirely.
Sure.
Yeah. Well, it's kind of related to one of the first questions. This is a collective problem, and it's about establishing new norms. A comparison that's sometimes made, it's like sort of piracy in the 16th, 17th centuries, where nation states were not cooperating and piracy was a legitimate state activity. Right now we have a few states, sort of specific states, that are not being responsible, that are tolerating large-scale commercial cyber hacking groups in their territory, and they know about it. So, there's a kind of, it's a question of putting pressure on those states at a sort of international level, all the way down, until we create a new social norm. And like piracy, with states, and we can do it with something like airline travel, postal systems. We've done this in the past. We've established new norms of international cooperation. And when you post a letter, you expect it to get there, and it typically does. These were international norms established in the sort of 19th century. So we can establish better norms by which we would cooperate and not tolerate states harboring such activity.
Dave?
I agree, but I'll go a step bolder. Every government in the world is involved in hacking. Whether it's perceived over here in the Western world as good hacking or bad hacking, they are all doing it. Law enforcement can't make any progress until there is international cooperation. The only way to investigate and bring people to justice is by having the diplomatic supporting mechanisms to allow you to bring other people around the world to jail. And to the gentleman's point right at the start, the governments around the world, while the internet has yet to grown up, feel that it is a reasonable economic burden on citizens and corporations to allow the basic attack fest that goes on from nation to nation and nations against citizens. And until that changes, it's just going to be a technical battle and many of the measures that Grace was telling us about.
Great. There's no way to sum up what we heard on the panel, but if there's one lasting thought, it might be this. There's probably two kinds of problems in the world, some problems that you solve and other problems that you manage and you actually never solve, and clearly cybersecurity fits into that latter category. Please join me in thanking the panel.
Stay there, stay there. Thank you so much. That was absolutely wonderful. Guys, you know the drill now. There's a Meet the Speaker session. I think that Robert and Grace are able to stay. And Tom is over there holding the sign. So if you'd like to go and continue the conversation, please do so. But remember, this stage is going to get absolutely rammed. So you might want to hang on to your seats. We're going to have a 2-minute turnaround just now before we get on to the next session, Complexity, Information and AI. And then, of course, we've got Thomas Reardon coming at 12:30. So, see you shortly. Hi, hello, come on in, get set down. There's some seats over there and right at the back over there. We're here for Complexity, Information and AI. We spent the first day looking at foundations, the second day looking at applications, and now we're going planet scale, or at least I hope we are. We're going to talk about the economy. First up, we've got Tora Greipel. He is research group lead at DeepMind and a professor of machine learning at UCL. So would you join me in welcoming him to the stage?
Thank you. Thank you very much. Great pleasure to be here. Good morning. Thanks for showing up. Yes, I think we have a very exciting topic, and I'm actually going to argue for something that is somewhat unusual, I think, for computer science circles. How do we create more complexity? Because we would like ultimately to create artificial machines, and the paradigm we use is machine learning, but where will all the complex interactions come from that enable us to train such machines to become intelligent? And I'm going to argue that it is multi-agent learning that we need to do. We need to put many of these machines into a box and let them interact, just as we learn by interacting together. Okay, so before we think about how to solve intelligence, if you like, what is intelligence? And I like to refer to the definition by my colleague Shane Legg here, who has been arguing that intelligence measures an agent's ability to achieve goals in a wide range of environments, to solve many different problems. And he also has this formula that quantifies that, but I'm not going to go into the details here. But if you think about this definition, and if you think about a learning-based approach to intelligence, then clearly the question comes up, where do the learning environments in which these agents act come from? But first, let's look at the agent and the world. So on the left here, you see a learning agent, a neural network, and on the right, you see the world. And typically, we work in the reinforcement learning framework. So the agent observes the world and takes actions, and then also receives a reward, depending on the outcome of that interaction over time. So that's the reinforcement learning paradigm. And the agent needs to discover policies, ways of behaving, in order to maximize long-term goals or rewards. And here you see some examples of environments that have been created by DeepMind. This is called the DeepMind 30 lab, where designers have created specific environments in which these agents that observe the world can interact and learn how to do things, how to navigate mazes, how to find treasure, how to solve test questions, and so on. But you see, this is just not scalable, because we can't just continue developing smarter algorithms and at the same time create more and more complex worlds. Every single one of these scenarios is basically a mini game. We'd have to hire all the games developers in the world to do this. And so the proposition is, let's put many, many agents into one environment so that they can pose problems to each other while they're learning. And that's basically an ecosystem of multi-agent. And I'll give you two examples of where this has been done. One of them is AlphaZero, which is the successor, of course, of AlphaGo and AlphaGo Zero, those systems that beat the strong Go players at first at the game of Go, and then in AlphaZero in the game of chess. And so this is, in some sense, the simplest version of a multi-agent problem. It's a two-agent problem. You know, going from 1 to 2 can make all the difference, though. And so what you see here is the basic architecture. There's a learning agent at the top, and there's two versions of it, one playing black and one playing white, and they play against each other. And as they play, initially, there's nothing great happening. They're playing randomly. But at some point, the agent stumbles upon a victory. You know, by chance it wins. And that's when the magic starts happening. That's when these algorithms learn, and they learn to make the better moves that lead to victories, to make them more likely in their play, and the less good moves to make them less likely, so they become better and better over time. And then we tested this system, AlphaZero, against Stockfish, which is a very, very strong chess engine that has been engineered based on mostly on search and designed evaluation function. And it turned out that AlphaZero, the system that has learned just by playing against itself, millions of games, mind you, can beat Stockfish many more times than Stockfish can beat it. Of course, chess is a drawish game, so there are a lot of draws at that high level of play. And so even Kasparov was very impressed. I think maybe the greatest compliment that he could make to the system was that it plays a bit like himself. So just to summarize this, in 8 hours, AlphaZero learns more about the game of chess than humanity has over the past 1,500 years. And that's the result of self-play, of two agents playing against each other many, many times to explore this world, to pose problems to one another. A second example, Capture the Flag. This is a completely different game, and in which two teams compete and need to capture the other team's flag. Here's a little tutorial. On the left, you see the agent perspective, and on the right, you see a top-down view. And you see these blue guys need to run to the opponent base and pick up the red flag, and then return to their own base, and they score if they can take it to their own base, but only if their own flag is still there and the opponents hadn't captured it in the meantime. This is a very complex task because the agents perceive the world incompletely, just from their first-person perspective. They need to cooperate with their teammate. They need to find ways to compete against the other team. They need to find those flags and bring them back. And to make things more difficult, we did this not just in a fixed map, we did it in a large collection of randomly generated maps, so that every game for them is different. And they cannot just learn one map by heart, but they need to learn how to explore maps. And we also trained them with different teammates and different opponents, to the point that they can also play with humans. And in fact, it turned out that humans preferred playing with the trained agents because they were so skillful and reliable in their behaviors. And when we did a test on individual behaviors, we found that these agents that were trained in this way, by playing in these various combinations against and with each other, they found these really fascinating strategies. They defend their home base. They really team up to do that. They do opponent base camping. They wait in the opponent's base and wait till the flag comes back there, and then they steal it and come back. In the meantime, the other agent already goes to the base again to steal the next flag. And finally, they follow their teammate in some scenarios, so that there's two agents that can work together because they're in the same area of the map. At least, I mean, those are my interpretations of that behavior. Good. And finally, these learning agents were really good at what they were trained to do. In a fixed pool of opponents, the learning agents won 74% of their games, whereas strong human players only won 52% of the games. You know, it's still close, but, you know, should be fun matches. Okay, let me conclude. We believe that reinforcement learning is really a phenomenal paradigm for studying artificial intelligence, for creating artificial intelligence. But we need two things for them if we just use a standard paradigm. We need to develop stronger learning agents, neural networks, if you like, that can learn how to behave well. And we need to develop more and more complex environments, almost like a school curriculum. We need to build these worlds that guide our agents, enable them to learn more and more things. But that's not scalable. And what I'm arguing here is that just as evolution created us in a multi-agent process, we need to put these learning agents together so that when they learn together, they pose problems to one another, just like one chess player did to the other in the AlphaZero setting, or one team of Capture the Flag players for the other one. By changing their tactics, they challenge the other team to invent new things, to be innovative, to find new solutions. And we've shown this actually works in practice in such diverse scenarios as chess, Go, and so on, but also in video games like Capture the Flag. So in the future, where can we take this? We will hope to build more and more complex worlds in which these agents learn to interact, solve more challenging tasks, maybe find niches and specialize, and where we can also understand how initially selfish agents can get together and cooperate. Thank you very much.
Thank you, Tor. I'll take that off you. Thank you very much. So, Tora wants more complexity. I'm wondering whether our next speaker, Eric, wants less. Eric is Professor of the Blavatnik School of Government and Executive Director of the Institute for New Economic Thinking at the University of Oxford. Welcome, Eric, to the stage.
Thanks, Azeem. Good morning. As an economist, I have to admit I'm feeling a little bit out of my element at an AI conference, but I'll note that in college I wrote a Lisp program that could play a pretty decent game of canasta, but things have moved on a bit since the 1980s when I last delved into this world. But I study the economy as an evolutionary complex system of networked intelligent agents, and so I'll talk about how that might be relevant to this topic. So this is a nice picture of some weaver birds doing a pretty intelligent thing, building a complex nest. Now, we know that the natural environment is complex and creatures need strategies for surviving in that complex environment. And evolution works through a process of niche creation and niche filling. So as the niches that allow simple strategies get filled up and more competitive, this creates pressure to create more complex strategies, which in turn create new evolutionary niches. But complex strategies require different forms of intelligence to manage them. So this creates a bootstrapping dynamic where intelligence emerges from complexity. But intelligence also creates its own complexity, particularly when you get to social creatures like these chimps having a meeting over that nut. The environment these chimps live in is both a physical environment and a social environment, and they need to navigate both to survive and reproduce. But the complex social environment is self-created by the chimps themselves and their own intelligence and co-evolves with them. Now, things get really interesting when survival is not just an individual matter, but also a function of your group. Then there's really huge evolutionary pressure for complex social structures that promote group cooperation, and then the intelligence needed to create and navigate them. And researchers think that human intelligence evolved out of an arms race between our brains and our complex social structures. Now, we can see these kind of dynamics in a very abstract way in a simulated environment. This is a classic study from the 1990s of agents playing prisoner's dilemma on a lattice. And the way it works is you live or die depending on your score in the prisoner's dilemma. And if you live, you reproduce into your neighbors who died. And you start with random strategies for the prisoner's dilemma, but then there's a genetic algorithm that allows the creatures to search for new strategies and critically also allows their memory to grow over time. And in this very simple evolutionary game, you see the emergence of more and more complex strategies over time. And you see even regimes where a strategy comes up and dominates for a while, and then a new strategy develops, the old strategy dies off, a new one comes in. So you see this process of niche creation and niche filling playing out over time. And you not only get the emergence of complex strategies from this very simple game, but you even get the emergence of cooperation, where agents will band together to play cooperatively the game and then keep away agents that are defecting. So from a relatively simple game, you can see this bootstrapping dynamic of complexity and more complex strategies. Now, we can think about very much as Thor described in his talk, that we can see new ways of developing learning in artificial systems. So the traditional approach of AI and machine learning is to sample a complex space. We take data from the world and we train an algorithm on that data to produce some result. And as DeepMind has shown with its amazing AlphaGo Zero and other experiments, we can also have these learning games where you have two agents playing each other in a game, learning the rules of the game and learning, exploring the strategy space and learning very effective strategies. But we can also imagine another approach where we start with a population of agents, of heterogeneous agents, and we allow them to play in a set of games in the strategy space, but we also allow that strategy space to evolve and create more and more complex games and more complex strategies, again, in this evolutionary bootstrapping dynamic. And that, just like the slide with the prisoner's dilemma, will create these complex emergent dynamics, which then feed back into the agents as they learn from their world and their environment. Now, we can be inspired by this natural process and use technologies like agent-based modeling to model this in social systems. And our work at Oxford, we use the economy as a lab for this kind of approach. One can think of the economy as a set of complex games within complex games that are self-created by all of us. The economy is a set of social structures that emerges out of our ideas, our heads, our strategies, and we create the rules of the game in economic systems. This is a paper where we did some work with the Bank of England simulating the housing market in the UK. Housing was a huge factor in the financial bubble and crash of 2008, so we built a fairly realistic simulation of the UK housing market using lots of data on households and banks and real estate and so on. And then we created a set of agents that could explore this model and help the bank look at new potential policies to reduce the booms and busts in the housing market. And it produced some very interesting results. Now, we also did use some machine learning to sweep through the model and look for its dynamics and where it was stable and unstable. But we could also imagine using AIs to play the housing game and look for new strategies and new rules, which could either be valuable if you're, say, a real estate investor, or it could be valuable if you're a regulator like the Bank of England. So we can start to create a vision for a next generation of economic models using these techniques. So we, again, start with a set of agents. They could be adaptive behavioral agents. They could be human players. They could also be AIs. We then can set up in the model the rules of the game, contracts, markets, information flows, and even physical geography. In the housing example, geography is an important factor. And then emerging out of these interactions, you get the macro behaviors, economic growth, business cycles, leverage cycles, economic inequality. We're also using these techniques to understand the transition to a zero-carbon economy. And then you can explore these models and explore agent behaviors to both get a deeper understanding of how these systems work, but also for many public policy applications. Again, the Bank of England model is just a small example of that. But we're looking more generally at how to mitigate financial crises, issues of economic inequality and opportunity, monopoly and market power, innovation and growth, and so on. And there also may be a number of private sector applications. A number of hedge funds are very interested in these ideas, also retail, e-commerce, manufacturing, and energy. So just to sum up, we can build realistic worlds a la the video games that Tore just showed, but we can build realistic worlds that look like the real world of our social and economic systems, and then use evolving intelligent agents to explore those worlds, develop new strategies, and also develop new rules of the game that can make them better systems for all of us. Thank you.
Thank you, Eric. Thank you very much. So AI to be able to build new ways of exploring complex systems like economics. Next up, we have Cesar Hidalgo. Cesar is the director of the Collective Learning Group at MIT, and he is founder of Data Wheel. Welcome, Cesar.
Thank you. So, when Fahrenheit started to explore the idea of measuring temperature, that was an idea that was not that easy to convey to people. Why? Because, well, at that time, the idea of temperature was not a concept that was quantitative like today. People thought that maybe in one room some people were hot and other people were cold, and temperature at the end of the day, well, if some people are hot and some people are cold, it means that it's just subjective. Yeah? But eventually, as they developed this capacity to measure temperature, Fahrenheit invented the mercury thermometer, people started to realize that even though you might feel cold and she might feel hot in the same room, temperature was something that was measurable. And my argument is that something similar is happening today to another concept, which is the idea of knowledge, okay? Not knowledge at the individual level, but at the social collective level. So during the last years, we've learned a lot about knowledge and about the properties that it has. If we have to measure it, we need to understand a little bit about it. And the first thing that we know is that first, it's non-rival. What does that mean? Well, it means that as many people can use it without taking the use of other people away. So a hammer, that you're using to build a birdhouse is a rival good. If I'm using the hammer, you cannot be using that hammer. But the idea of the birdhouse is something that you could be using at the same time as me without taking it away from me. Also, knowledge is not just simply additive. It's not just simply extensive. So if we're going to think about knowledge at the collective level, we have to figure out more interesting ways of aggregating than just adding it, okay? So if I know how to make shirts and I know how to make pants, and then I learn how to make blouses, I didn't increase my knowledge by an entire new unit. There's a lot of redundancy in knowledge, especially between similarly related activities, and hence, you cannot simply extend it. Knowledge can be tacit, can be explicit. There's some things that I can learn through acts of communication, and some things that I cannot learn through acts of communication. We could bring Messi to speak at CogX all day about soccer, and I'm sure that the moment that you leave the room, you wouldn't be better soccer players, because that type of knowledge is tacit. It's something that gets acquired through experience in the context of social learning. Knowledge diffusion is also very limited, but knowledge, more importantly, varies also in its degree of complexity. So if you have an orchestra in which every musician is very well trained and every instrument is of high quality, but all of the instruments are the same and every musician only knows how to play the same instrument, well, the complexity is going to be much lower than if I have an orchestra that has sections of brass and winds and percussion and so forth. So one of the things that actually matters is that in some way when we think about knowledge, we have to figure out this knowledge that allows to do a large diversity of things. So the question is, how the heck we measure this knowledge? We know that it has all of these properties. We cannot simply add it and so forth. It is tacit or explicit. It is non-rival. But how do we measure it? And one way to try to measure knowledge is by looking at the things that places or people know how to do. So, well, how do I know that Germany is good at mechanical engineering? Well, because they export a lot of products that are intensive in mechanical engineering and so forth. So we can grab data on the activities that are present on locations to create very detailed indicators, of the knowledge that may be available in them, and we can use this to compare knowledge and to make predictions about the future of these economies. So there's a few measures that we developed over the last decade. One of them is the idea of relatedness. And this is the idea that knowledge is not something that you have or that someone has. It's always something that someone has about something, okay? So you just simply don't have knowledge. You always have knowledge about something because knowledge is specific to activities. It's not kind of like this general glue. So if you have, let's say, 2 cities or 2 countries that have certain industries that are present in them, that is going to imply that some other industries are going to be related or close by. These are industries that are going to share many of the inputs, that they need with the industries that are already present in them. So with that idea of relatedness, you can predict what are the activities that a place is going to enter or exit in the future. Here you have an example of the economy of Chile diversifying between 1979 and 1996, and you see that the products Chile enters to during this period are products that are close by or related to the products that they were doing in the past. So that's something that by now we know in the literature to be generally true. And there's a principle at play here. It's kind of like a new law of gravity, but in this case, it's a law that rules, the activities that economies are going to enter. This is called the principle of relatedness, and it's true at a variety of spatial scales and for a variety of activities. You want to know what are the areas in which your university is more likely to start publishing in the future? Well, those are areas that are connected to the areas, where you publish today. You want to know what are the industries that your city is more likely to exit in the future? Well, those are the industries that are going to be isolate on this relatedness space. But also we need measures that are aggregate, that are not just about the knowledge that you have about something, but the one that you have in total. And this is the idea of having measures of complexity. So how do we do this? And this relates a little bit to some techniques that are similar to more traditional forms of machine learning, like dimensionality reduction and so forth. So what you're going to say is, well, how do I know if London is more complex as an economy than Barcelona or Tokyo or Manchester or Paris? Well, one way to do that is to say, well, let's look at the activities that are in London, and let's say that the knowledge complexity in London is proportional to the knowledge complexity of its activities. Okay? So I'm going to say that the knowledge K of a city C is proportional to the knowledge K of the activities P that are present in it. Now, how do I know if, let's say, software development is a complex industry and garbage collection is not? Well, I'm going to say that these complex activities can only survive in the places that have the complexity that requires them, that they require. So I'm going to say that the knowledge K or the knowledge complexity of an activity P is proportional to the places where this is present. And if you do that, you get a self-consistent equation in which you can actually solve like an eigenvector problem in which you have the knowledge of a place is equal to a function of the knowledge of the place. You can solve that using, eigenvector algebra or iterations, and you can get a measure of the complexity of a location, and similarly of the complexity of an activity that doesn't require you to make any assumption a priori of which activities are more sophisticated than others. And this is nice because it gives you like a bunch of bonuses, when you solve kind of like that little matrix equation. The first one is you have something that predicts, at the international level, the level of income of countries and their future economic growth. So you have a measure now of the knowledge that a country has, and the countries that have more knowledge per unit of GDP per capita are going to grow faster. So in this framework, the growth of China is something to be expected because the cost of knowledge in China is very cheap. They have a lot of knowledge per unit of GDP per capita. It's not a matter of labor cost, it's a matter of knowledge cost. Also, you can explain very well international differences in income inequality. It's really hard to have a society that have low levels of income inequality, when you have the productive structure of Peru, or Nigeria, which is very geared towards extractive resources. It's very hard to have a high level of income inequality with the productive structure of Sweden or Switzerland. There's a coevolution here at play, in which actually, income inequality is connected to the complexity of activities. But the last thing I'm going to leave you with is a more recent result in which we have been trying to understand how the complexity of knowledge relates to the spatial concentration of activities. And why is this? Because, well, we live in a world in which spatial inequality is one of the most important topics of today. Cities like London are doing great, but other places in the UK are not doing that great. Is this something that only depends on policy? Is this something that is about choices that we made, or are there some sort of natural economic forces that are creating this divide? So in this map, you see the patenting activity of the United States. And you see that there are some places in the US that patent a lot, like San Jose or New York, Boston, and Chicago. But most of the US doesn't patent at all. So the spatial activity, especially innovative activity, is very concentrated. We know that for a long time, from the work of Marianne Feldman and others. And one way to study that spatial concentration is to do a simple chart in which you say, what is the population of a country, of a city, how many patents they produce, and you realize that actually, when you do this in a log-log plot, you get a coefficient that is like around 5/4. What that means is that the larger cities do more patents per capita than the smaller cities. Okay? But you can grab that and you can start disaggregating, let's say, those patents or economic activities into different categories. And you realize that the patents in computer hardware and software are much more superlinear than the ones on pipes and joints. So patenting activity on pipes and joints is distributed more or less similarly to population, but the ones on computer hardware and software are much more concentrated on large cities. And you can do that for patents, you can do that for papers, you can do that for industries, you can do that for occupations, and what you find is that along all of them, if you take some sort of measure of the knowledge intensity, of those activities or the complexity, you find that the more complex an activity is, the more it concentrates in space. So what this is telling us is that, well, if we're moving faster and faster towards an economy that is very knowledge intense, our economic activity is going to continue to concentrate in cities, and we're going to have to start thinking about, well, how do we include more people into the cities that we have instead of trying to develop, the places that are left behind, because that's where the economic activity that we are doing right now is taking place. So these are just a few lessons of how knowledge is being transformed from a concept that it was more ethereal or qualitative into something that is more quantitative and is helping us understand the future of our economy. Thank you. We stay up?
Cesar, stay here, please. And Eric Toro, please join us on stage. So we've got about half an hour, just under half an hour, I think, to try and delve into some of the issues and interests that were highlighted by your presentations. But I hope you're all going to forgive me for a really boring opening question. I feel like we need a local definition of complexity. So when Tora was talking, I got a sense that complexity for you means something a little bit akin to cognitive load. So the complexity of the environment and the number and types of interactions within it. Whereas complexity seems to mean something maybe a little different in the realm of economics. Is that true?
It's a good starting point. I think in some sense we view complexity as this useful thing, almost like the kinds of problems that an environment poses to a learning agent, because unless the learning agent gets exposed to interesting problems and learns how to solve them, it can never become more intelligent, if you like. But of course, there could also be an overload in complexity. So, for example, if you imagine a school curriculum with more difficult topics being layered on top of simpler topics. If you jump in at the wrong level and go to some kind of graduate level class first, then as a learning agent you will not learn much. And so in some sense we would be aiming at a layering of more and more complexity that these agents would be exposed to.
I think there was actually a nice connection across the three talks, because one way to think about it is it's a search through some huge combinatorial space. What gives the high cognitive load of chess or Go is you have this huge space of possibilities. What I was talking about was how evolution searches spaces of possibilities to then create strategies for managing that, which co-evolve. And what Cesar was showing us with some very nice data was that the product space of the economy is this huge combinatorial space, and we can think of economic growth as a search through that space of all the possible products and services we could make.
Yeah. So a lot of definition of complexity hinge on the fact that systems that are complex can adapt and evolve and have multiple parts and so forth. The one that I like the most is the one that was proposed by Warren Weaver in a classic paper on the 40s, he says that science went through like 3 eras, The first era was the science of simplicity, which is when people discovered that you can describe nature using trajectories, okay? So that's basically physics, and differential equations and all of that. And that science gets into trouble during the 19th century when, all of the craze was not about cannonballs, but was about like heat engines, and they need to develop thermodynamics and statistics, and that's another science that is based on another math, in this case probability and statistics, that allows to deal with systems that have what he calls disorganized complexity. Because these gases or things that if you change the elements involved, you change an atom here by an atom there, it's the same. It's a gas, it's like the statistical property what matters. And what he said that was happening during the middle of the 20th century was a transition to try to understand systems of organized complexity. And to him, these were systems in which the identity of the elements involved and their pattern of interactions cannot be ignored. Okay? So society, biology are systems of organized complexity. The economy, of course, is a system of organized complexity. If you change one protein type by another protein type, the whole cell, might die, or you might get a disease. So,
just to be clear, are we agreeing with Eric that it's about the complexity of the search space?
Yeah, in part, yes. Yeah.
I didn't mean to cut you off, but I felt like we might be going down a rabbit hole, and I was trying to increase our common understanding. Yeah. So thank you for that. Now we're all clear. Excellent. Let's move on. And first off, there were, at least with Tora and Eric, your talks, there seemed to be quite some similarities in the sense of you were each talking about the co-evolution of intelligence and complexity. Could you speak to where the similarities and maybe some dissimilarities in your approaches are?
Yes, so I think I focus mainly on systems with few agents, where each agent has a higher degree of internal complexity, a higher cognitive capacity, if you like. In chess, there's 2 agents, if you like. In these capture the flag games, there are maybe 4 or 8 or 16 agents. And so for us, that is interesting because we're interested in growing the intelligence of each of these agents involved. And so we want them to have capacity to express more and more complex strategies. To play chess better, clearly you need some degree of complexity there. I think that's in contrast to what Eric was proposing, where the focus is on looking at more agents that have lower complexity individually, but that can collectively create interesting macro phenomena. And I think there's an interesting interpolation possible between these spaces. We would certainly also be interested in maybe inserting some of our agents with more learning capacity into such simulations, although at some point we might run into some computational limits. But I could imagine, for example, that could be bridged by creating cohorts of identical agents that represent groups of a population that behave in roughly the same way, but then could, because of an increased cognitive capacity in the model, maybe come up with more interesting innovations.
Yeah, no, I think that's exactly right. We're sort of working at 2 ends of the proverbial telescope, and we're building models with lots of agents that we're trying to make behaviorally realistic enough to capture key elements of the phenomena, but are not nearly as intelligent as the agents that Torre is working with. And these models can be quite large. One of our collaborators, Rob Axtell, has built a model of firm evolution that has 120 million agents, representing 1 agent for every worker in the US. And they're relatively simple agents, but out of that he gets macrodynamics that look very similar to the real-world macrodynamics of firm growth and evolution. But you can imagine, as we have more and more computational power, you be adding more agents and playing other kinds of games, with the AI approach, and we're adding more intelligence, behavior, to our large agent systems. And then as they start to meet in the middle, we get things that actually look like what's in this room and what's out in King's Cross in the economy. And then we've got this amazing laboratory to be able to explore real-world phenomena with.
It seems like a good time to talk about how much do observations of natural intelligence, knowledge formation, inform AI research, and vice versa? How much are the 2 fields interacting?
Yeah, at DeepMind we're a big fan of that connection, and it constitutes one of the bases of our work. So I think roughly the argument is very simple. We have 1 proof of concept that human-level intelligence is possible. It is it's the human mind, and in association the human brain. And so if we want to engineer an artificial intelligence, it makes every sense to peek over to our friends in neuroscience and work with them to understand what are the principles that make human cognition possible, and which one of those principles can we use in creating an artificial agent. That is such a fruitful endeavor, and the art here is to find the right level of abstraction. So does it have to be biological tissue that produces intelligence? Probably not. But if we move a couple of layers up, if we see specialization of regions in the brain, then we can find very interesting correspondences. And these have in fact been made with reinforcement learning and the dopamine systems in the brain, or with convolutional networks that were inspired from how the visual cortex works. And I think at that level, that makes a lot of sense, and a lot can be learned from that. And I'm sure that's true also for more of the macro level of systems.
So Eric, of course, did talk about agent-based modeling and evolutionary strategies in your work. Cesar, are you using machine learning?
Yeah, I do a lot of applied machine learning. I don't do fundamental research on machine learning, but we do use it a lot. And part of the way I think it connects to your question is that at the end of the day, the whole trick is always to have like the computer learn from examples that come from, in some way, human intelligence, except when you're having them play against each other, of course, But if you read How Smart Machines Think, which is a nice book that introduces people to AI, they show that the big breakthrough in the self-driving car is from going from this idea of trying to engineer intelligence through mapping and features to basically having people kind of drive a car with a lot of sensors, so then the car would learn what parts of the road are acceptable or not acceptable. And I do think that feedback loop, that fact that machines are learning from our behavior, is something that is fundamental and is going to stay as part of the loop for at least the next decade. Yeah.
Perfect.
I've just had one more connection that the historical approach in AI and machine learning has been essentially to learn from a world that is fixed. We sample some data, which is a kind of snapshot, maybe at a period of time or something, try and learn from that, or we learn from a game like chess, which has a fixed set of rules. I think that the next approach where we can learn a lot from evolutionary systems is how do we learn and innovate new strategies where the world itself is evolving.
Maybe one word about what Cesar said, because I think you're right, and it's quite fascinating that we can, in some sense, do imitation learning and learn from the patterns of humans. But what we found in our work on AlphaGo, AlphaZero, and those systems is that while initially it was really helpful to do imitation learning based on, for example, human Go games or chess games, it also constituted a constraint on the system. And so when we let go of that constraint, once we had learned how to train these systems and just let the system play against itself, given just the rules of the game, it actually became stronger than human players. So it wasn't limited, so to speak, by the existing knowledge. It built its own treasure of knowledge by just playing against itself. And then what we found particularly fascinating in working with those communities of chess and Go players, of course, we shared that with those communities, and then those humans started learning from the machine and picked up patterns that the machine had discovered, and then started using that in their own games. So machines by themselves, if you like, can go beyond the knowledge that has been created by humans, but they can also feed it back and then enrich the human community.
Our search space as humans would be a little bit too limited and constrained, which would be an interesting cognitive science finding, that we basically don't explore the full space and we kind of get stuck in this local optima.
Yeah.
That was, I think, Eric, what you were suggesting we might help us to uncover new economic models.
Yeah, well, a challenge in understanding economic systems or any social system is, again, the system is self-created by all of us. You have the interaction of intelligence, creating the structures and the rules of the game that the intelligence that has to navigate, and then that feeds back to change the structures and the rules of the game. Being able to simulate those systems and then have AIs explore them offers a range of possibilities, both for understanding the systems, but also for training AIs in different ways. You can think of, Thore showed creating a video game world for AIs to navigate and explore. Well, you could also create a world like the housing market or the transition to a low-carbon economy, for those agents to explore. And just as in the Go example, it's quite likely they would come up with things that we haven't thought of.
So I guess that leads us to the next question. I opened this session by rather facetiously saying that we're going to talk about planet-scale problems now. What can machine learning, reinforcement learning, AI do for questions of the environment or for the economy? When will AI actually be in a position to do something useful, to provide us with some insights, be able to model those really very complex adaptive systems?
I think Eric's work is a great example of that, because
so it's already happening.
In some sense, yeah, it's already.
Well, I'd say it's still more in the vision and slightly hand-wavy stage than reality at this point. But I think the vision is quite a concrete one, that we now know how to build actually quite high-fidelity models of real-world phenomena through these multi-agent simulations, and quite importantly, the kind of micro-granular data that didn't used to be available is now increasingly available, and the compute power is now available to do that. And we have some visions about how you create software libraries and structures that can be like Lego sets to assemble these complex social models or economic models. But then I think the next step is to start bringing in some of the learning and AI techniques from things that like what you guys are doing into those models. Probably baby steps at first, because again, there's limits to compute power. But I think we would learn a whole lot from that kind of experimentation.
If I can add a little bit to that, so I do think that like at the moment, in all of these examples in which we have like multiple agents learning, we still have like multiple agents learning within kind of like one God. There's one person or programmer or group of people that created them. But I think the breakthrough where we have to go next is a world in which it's not that Eric makes one agent that represents me in his computer, is that there is an agent that represents me that exists in some sort of instance in the cloud that can collaborate and interact with the agents that represent Thor, and there's some way for these agents to have access to our data in some private form, in a way that we can always like pull it back and so forth. And in that world in which all of us have those digital twins that are helping us shop in the supermarket, arrange meetings with one another, and do many other things, we might have an emergence of solutions and complexity and a public sphere that is empowered in a different way.
Our own digital twins.
Yeah, exactly. Yeah.
Okay.
Yeah.
Well, and to Torre's point about humans also learning from these algorithms and AIs, in these simulations, you can have human players as well, interacting with the AI players. And that creates another set of interesting opportunities to learn.
And Eric, you made this interesting point that also the rules of the games can be changed.
Yeah.
And I find that very fascinating, and we have some work on this. For example, you can think of two agents or more agents that could be caught in some kind of social dilemma, in a situation where, like a prisoner's dilemma, where they could be caught up by the fact that each one of them wants to behave selfishly, but if they both behave selfishly, they actually end up in a worse spot than if they both cooperated. And that is actually a fairly common situation if you have groups of selfish agents interact, for example, in the economy. And AI systems could also be used to help us get out of these situations. You can think of some kind of a governance mechanism that could be learned that could provide just the right incentives for agents to start collaborating. And once they're in this equilibrium of collaboration, maybe it takes very little to keep them there. And so we could all get into a more harmonious mode of interaction if we were just nudged that little bit into those equilibria that we would like to be in anyway, that we're just struggling to find collectively because of our kind of egotistical limitations.
Well, and I'll give a real world example of how that approach might be useful. So we know that to transition to a zero carbon economy, we need to change the rules of the economic game, and economists have a favorite answer to that, a carbon tax or a carbon price. But we're doing some work trying to understand the system, which has different regimes, tipping points, dynamics, and we know these systems can be sensitive, where small changes in the rules in different places can tip you into a different regime. So can we, by building high fidelity models of the system, actually find those what we call sensitive intervention points, where we could think of new rules of the game, that would tip us into that regime, more quickly, at lower cost, and more effectively than perhaps other policies would.
Would you like to respond? And then I have a cracking question.
I do think that, like, in some way, we might be getting a little bit stuck in the context of the representative agent, because at the end of the day, we could do a very advanced simulation, that is based on some agents that were created by someone, but that doesn't mean that those agents reflect the preferences and the diversity of preferences that people might have. I might be a guy that, let's say, in the context of sustainability, I like to eat a lot of meat, so I don't care about that part, but I'd be okay with getting rid of all plastic. Well, what's the frequency of guys like me in society or people with different preferences? That's why I do think that at some point there has to be a transition in which the agent is connected, to high fidelity adaptive data about society, so that that diversity of preferences can be incorporated, because otherwise you're going to end up coming up with solutions and equilibrium for agents that are not the ones that reflect us. And that link between the agent and the human is something that at the moment, it's a little bit missing from this silico to data world. But I do think I talk a lot with private sector companies that are going into like the digital twin space in the next decade, and I think there's going to be a lot of competition there. Yeah.
Okay, I'm going to just try to, we've only got 3 minutes left. I don't know how it went so quickly. And Azeem whispered in my ear, so I'm just going to pose this question, but maybe you can answer it afterwards in the audience.
Sure.
because I wanted to get onto the spatial inequality question. And Azeem pointed to your slide you had up with the Ballard et al.
Yep.
And he said, that right there explains Brexit. So don't answer that now. I think perhaps that's something we can talk about later. I want instead to give you each a chance to just do some closing comments. So perhaps 1 minute each. And then, as always, guys, there is the Meet the Speaker session afterwards. So I hope you'll continue the conversation. Tora, can we start with you?
Yeah, I think it's a time of immense opportunity. We're building these more and more complex ecosystem, and we can benefit, I think, from various different angles, and this discussion has shown that. While we might be focusing on the intelligence of the individual agent that can grow because of the rich interactions with other agents in that ecosystem, we can also take the macro view and zoom out of the system and use it to understand what would happen in terms of qualitative behaviors that emerge in these complex systems. And finally, we might be able to connect these actors, these agents, to actual actors and get even more precise views based on people's preferences to understand what's happening both at the macro and the micro level.
And I just close by saying, I think what this session has made clear to me was, we've had these different research streams on AI and ML, multi-agent systems, understanding evolution from a kind of algorithmic computational standpoint, and that bringing these three streams together is a hugely rich area that hasn't really happened yet, but has a lot of potential. And I think to Cesar's point is exactly right. To do that is going to need a lot more data that we currently don't have and a lot of compute power, but those things are increasingly available. And if we pursue that agenda, there's huge possibilities both for bettering our social systems and policies, but also probably some pretty exciting commercial opportunities as well.
Like technology can be exciting, can be frightening, but you shouldn't ask apples from the oak tree. So I do think that at the end of the day, AI and technology is going to help us, optimize a lot of things, but they're not going to make us happy. Happiness happens when, the lights are off, you go home, and you have the same people, to hang out every day. And a little bit, I think that's something that sometimes we lose. And I live in the US, I've been there for 15 years, and everybody's always trying to find technological solutions to their emotional problems. And it doesn't fucking work, man. Yeah, it's like, it's about being with the same people all the time and getting to know each other and accepting their quirkiness and weirdness, and that's kind of like how you develop emotions. I think in Latin America, we kind of like have learned that quite well, nobody listens to us, but I think that as technology keeps on advancing, there's something there that we're going to have to rediscover in some places.
That's a good place to end. Let me invite Azeem up onto the stage.
Thank you. Thanks for the panel.
Thank you so much.
Thank you.
So that was pretty intellectually challenging. How many people found that quite stretching? Well, I'm really proud that we managed to keep 550 people in here for that amount of time. So you all deserve a round of applause as well. Our speakers actually have all got fantastic lectures on YouTube and TED Talks. So if you kind of have some energy on a Friday evening and you don't want to watch Netflix, just type in their names into YouTube. There are some really, really fantastic talks. We've warmed up your brain now. I just want to remind you that at 12:30 we have the last session of Cutting Edge, and we have Thomas Reardon, who's going to present some of his new technologies. Reardon is an absolute impresario and heavyweight in the world of human-computer interfaces. He designed a web browser that was used by more than 1 billion people, and his new project is in the space of brain-computer interfaces and his new neural interface technology. Super excited to have him here. It will get crowded, but please make sure you are back by 12:25, 12:20, or even just stay through the break for that final session. And now we've got Meet the Speaker, I think, and thanks once again to our speakers.
Over there. Thank you so much, Eric.
Thank you. we're leaving the best to last. So thank you for staying with us, and thank you for braving the rain on the way in. We live in a world where we spend way too much time with our machines, often in quite unhealthy ways. And in fact, about 6 months ago, I had to stop weight training because I had a pain down my shoulder, down through my arm. And I spent some time in an MRI machine, and my orthopedic surgeon has said, too much of this has given me a slip disc in my C5 and C6 vertebra. So user interfaces, really important, can also be slightly harmful for us in some sense. I'm very, very excited about our closing speaker. Reardon is a giant titan in the world of human-computer interfaces. He's built products that were used by more than 1 billion people in the space of interfaces, in the space of browsers. I watched him talk, and I rewatched his YouTube videos, and he's one of the few people, when he's been on a podcast, I've listened to it twice. And so I felt I really had to get him here to close off the cutting-edge stage for CogX, and I'm really pleased to say he is here. He's going to talk to us about control labs and neural interfaces. Please put your hands together for Reardon. Thank you.
Thanks, Azeem. Hi. Thanks for staying till the end. I'm the CEO and co-founder of Control Labs, the company that spun out of Columbia University Neuroscience about 3 years ago. And we are building what we believe is the world's first pragmatic, broadly usable and broadly useful neural interface technology. There we go. I was looking for my cue here. So first question is, why are we at a point where we need to start developing neural interfaces rather than the traditional mechanical interfaces we use to talk to machines? The first thing I want to note is a kind of an obvious point to most working neuroscientists, which is that there's a huge gap between human input and human output. Your ability to take in information is extraordinary. Your ability to take it in visually, auditorially, proprioceptively from within your body. You take in tons of information every second, but you actually output a very tiny, tiny amount of information. And that's because you output by moving. You turn muscles on and off. And that's very slow compared to what your brain can actually do. So just to put it in context and put a number on it, someone theoretically established back in 2006 that the retina, just visual system alone, takes in and distributes into the cerebrum somewhere around 9 megabits of information per second. But your output, even if you're a really fast typist, peaks somewhere around 100 bits per second. That's pathetic. The contrast is shocking. And what it means is, in this world of new computing platforms, of pervasive computing that's on your wrist, or what I'll call augmented computing, like a robot or robotic buddy, or immersive computing as it exists in augmented reality and virtual reality. In all of those cases, we end up having to go through a sort of keyhole experience in which we're taking in lots of information, but we're not actually able to control it in a rich, human way, in what I'll call a high bandwidth way. We actually think these new platforms are begging for new kinds of interaction technologies that are no longer limited by your musculature, your ability to move. And I think more than that, I always think about this, that we grew up and then we regressed. With the debut of the iPhone back in 2007, I fundamentally think we regressed as a species. When I try to type on an iPhone, I'm not authoring, I'm shrinking down as a person, and I'm sitting there punching on the screen, trying to correct the autocorrector. It's this really cognitively demanding task. I am not more expressive. I am not more powerful. In fact, I've been captured by that device. It kind of owns me now. Control Labs is trying to reverse that equation. We want to build technologies that make your output quite a bit much more like your input. So how do we go about making ourselves more capable? The broad thesis is we use neural interfaces that we directly connect to the brain. We extract information from the brain, your intentions. The problem is, we've been talking about this maybe for a century in the science fiction literature, but there's no real easy way to go about doing this. And today, I'm going to review a bit of the different approaches that people are taking to neural interfaces, brain-machine interfaces. And then I'm going to introduce you to one that I think is going to scale out much faster and be much more broadly usable, and it's happening a lot sooner than people might think. So let's go on and review from a neuroscientist's point of view how you interface with the machine today. Well, first it starts with the brain, the cerebrum. You create an intention. That intention actually descends from motor cortex out to the spinal cord. The spinal cord is sort of the output interface of the brain, but it's still within the brain. And that turns muscles on and off. You do that when you're locomoting, whether you're doing skillful acts with your hands or your mouth. And then we designed a whole bunch of transduction devices, microphones and touchpads and keyboards and mice that take that mechanical movement and turn that into control signals over machines, the myriad of devices that we have in the world today. And that's pretty much how computing works. Any kind of digital device requires you to move laboriously or tediously to actually get that device to do something. And weirdly, they all require you to do something different. So the fundamental promise of neural interfaces is to stop talking about how you move and start talking about how you think. And to go into the electrical signals that actually are the signals that drive that movement in the first place, and query those signals and use those to directly control that myriad of devices in your life, no longer dependent on your movement. And now allow you to do things that you couldn't really imagine doing before with your own body, like what would it be like to have a sixth finger, just an extra one skillfully available at all times? Or what would it be like to kind of more exotically actually have 8 arms? And to feel like you have 8 arms, and to have that kind of facility in the world. So I'm going to walk through now and do a little bit of review of neurobiology. I know, looking at the attendee list, there's quite a few neuroscience people, mostly out of the computational world, but very few actually know much about the physiology of the motor nervous system, the thing that connects you to the world today. So first I'll go into BMI, brain-machine interface technologies, large overall, and I'm going to talk about sort of the substrates of them. So the first thing to introduce you is this thing called the action potential. So the action potential is the means by which 2 neurons connected at a synapse communicate to each other. One neuron on the left there gets electrically excited, it sends an electric pulse, and it's received, or excuse me, it causes a transmission of neurotransmitter at the little tip of the axon, and that's received on the downstream cell, and that in turn gets excited by lots of neurotransmitter being released onto that cell. It does some sort of calculation, and then it makes another signal downstream. It's pretty much the way the entire central nervous system works. Lots of different cell types, lots of different phenomena of signaling, but that's the basic picture. Now, within vertebrates, we have something called the action potential, the ionic action potential, and this is really interesting. What you'll notice is when a neuron is actually active, it has this little electrical pulse. But it's the same pulse every time. Every neuron has a signature pulse, an action potential. A neuron can't change the height, it can't change the width. It can only send the same action potential every time. That's true pretty much across the entire vertebrate nervous system, or certainly our nervous systems. And what this means is that the signals between neurons, and even between a neuron and a muscle, is what we call quasi-digital. It's really either a 0 or a 1. And the only way a neuron can communicate differential information is by changing the timing of these action potentials. But we're working with a 0 or a 1, which for most computer scientists in the world gets them excited immediately. So what people have done is said, well, let's go see if we can go figure out a way to get into the brain and go look for those 0s and 1s, those action potentials. And they've built these exotic arrays, Utah arrays, and other things coming online now that after surgery, this will be implanted. It's kind of a almost grotesque surgery. It's literally just a person pushing a comb right into your brain. And then they seal it all back up, and at some distance, you get to interrogate and listen to hundreds, if not thousands, of neurons simultaneously. And then you can see, you start to identify each neuron. These are actually the same pulses overlaid, and it allows us to see that different neurons have a different signature or different action potential form. And then we build up these systems that allow you to control, using some part of your cerebrum, a device. Now, this is seminal work from Krishna Shenoy, a lab at Stanford. He's one of our scientific advisors and on our board. And this is what happens when somebody who's lost all motor function gets one of these implants. And what they're able to do is to learn a crude way of controlling a cursor to type. Now, if you can't move, if you have ALS and you can barely even breathe and you're on a respirator, and you get a cursor, your life has changed. You have agency again. It took quite a while of time for this woman to get this level of control. She's here looking up things about one of her favorite topics, about taking care of orchids. But for that person who's lost all mobility, this is profound. But that doesn't scale to lots and lots of new kinds of interactions because you're limited basically by the surgery itself. So we start from a premise that these invasive techniques, while very interesting because they get to that signal of individual neurons, they don't scale because we're not all going to go through surgery, elective surgery, to be able to control a mouse cursor. So there's another field, subfield within brain-machine interfaces, what we'll call non-invasive interfaces, that try to find either signals, direct electrical signals, or proxies of those signals using other kinds of detection techniques. And those are broadly are classified under what we call EEG on the left, or another one called NIR, FNIR on the right. And I'll walk you through those and sort of where we are state of the art today. This is one of our scientists, actually a well-known EEG scientist who joined us a couple years ago, Alexander Barachant. So EEG tries to look at aggregate electrical activity of the brain. Not those individual action potentials, but literally hundreds of thousands to millions of action potentials all superimposed. And it does that by putting all these little electrodes over the skull and trying to look for big voltage fluctuations. And you kind of get a picture of big things that are happening in the brain. There are lots of things that hold it back from being a broadly usable technology. Number one, and almost humorously, is that there's a lot of signal conflict with what's called EMG, just facial EMG, that when your mouth moves and your head moves, your eyebrows move, you're also generating a massive electrical signal that dwarfs the signal that's coming out through the skull. The real problem with EEG is this. It's like you're sitting with a microphone in the parking lot outside of the stadium. Now, you're not going to be able to hear what this person up here in that row 7 next to this person in seat 3 is saying to each other. But you're going to know if somebody hit a home run or if there was a score. You know the big events, and EEG is very good at that. Are you surprised? Are you really stressed? Those signals are pretty obvious because they affect global brain state, but you wouldn't drive a car with it. The next one is FNIR and other similar technologies that are basically using light or magnetic resonance to find proxies of neural activity. And similarly, what you're reading here are, in this case, oxygenation levels that are correlates of neural activity within a subregion. The big problem here is that the temporal resolution is terrible. So that action potential I showed you earlier is anywhere 1 to 3 milliseconds wide. You can have 100 of them per second. Here, you're going to look at something where the signal is at about 1 second to 2 seconds, maybe 8 seconds. It's kind of smeared across the thing. And again, what you're going to find is, did somebody hit a home run? Did somebody just punch me in the face? Those kinds of signals are very obvious. They affect global brain state. But you wouldn't drive a car with it. You wouldn't try to type with it. You wouldn't try to do any of the fine controls that these new platforms beg of us. So, I'm going to skip some of this stuff around how BOLD works. There's probably somebody here in the audience who's an expert in it. I'm not. This is what the vasculature inside the brain looks like. This is the blood supply. And what you're really reading is how well oxygenated is the blood in different parts of the brain, because the neurons in that area are consuming it. But of course, the brain's a big place, and there really aren't specific areas in the brain for specific things that aren't affected by adjacent areas, et cetera. So you have this problem that BOLD signal, it not only is something that is smeared temporally and covers lots of function, but more importantly, it's not clear what function you're reading at any point in time. You're getting global state, but you're not getting that final, what I'll call micro state, that represents your incredible neural output capacity, that ability to actually control individual neurons. And that's where we come in. So we do believe in non-invasive, because that's how you scale to humanity. We also believe in invasive to the extent that that's how we proved in the first place that you could actually get control signals from individual neurons, that it wasn't just this chaotic noise, but that those action potentials represent decisions that you've made. Like, I'm going to turn left, and I'm going to go 20, now 25 miles an hour. These are complex decisions. They're outputs. The idea that you can map that to individual neurons is really quite exciting. And that's really the fundamental promise of all neuroscience, is understanding the translation of that neural activity to a final behavior. So here's the good news. When you extend the brain and don't limit yourself to just the cerebrum, you actually find what we'll call the USB port of the brain, which is the spinal cord. This is where you take in a lot of proprioceptive information about where your body is, but most importantly, this is how almost everything you do in the world is output. There's a small set of nuclei up in the brainstem that control your head and face. Everything else, including the most skillful part of you, right here, your hands, is controlled via neurons in the spinal cord, motor neurons, that send out axons and terminate on muscle and allow you to move skillfully. And I want to say this one more time. This is the most skillful part of you. The nerve density to your hands, really to your forearm, is about twice as much as all of that connects to your mouth for speech and feeding. It's where you have all your fine adaptive control. Something like your toes and feet are kind of dumb. They don't really do much. You send a signal to start walking, and you perambulate. And most of that happens without a lot of skill. But your hands can do extraordinary things. And I think we all intuit that. And in fact, most of our interactions with machines are based on the movement of our hands. Now we're seeing more speech involved. But again, I don't want to use my voice to drive a car. So we decided to go out and talk to those neurons and extract information from the neurons that live in the spinal cord. And the first thing we did, and I'm going to draw a contrast here between two different technologies that we built that are very complementary. One we call myocontrol, and the other we call neurocontrol. Now with myocontrol, we're taking the electrical activity that the muscles are generating, not as they move, but before they move. A neuron activates, it allows an electrical deflection, or causes an electrical deflection within the muscle, and that downstream, 100 to 160 milliseconds later, causes you to start to contract and move the muscle. We want to listen directly to that electrical signal and allow you to control things in the world in a way that we call biomimetic, i.e., as if you were moving, or you can be moving and doing it, but in which you get sort of finer control because you're no longer victimized by the actual speed of your muscles. So I'm going to show you some examples of that. One thing I want to point out, because my company is almost entirely an ML company, Most of the team comes out of the subfield of neuroscience called computational neuroscience, in which we build lots of computational models of how neurons communicate to each other and ultimately generate a behavior. Now, some of the big breakthroughs that happened in the last decade plus in machine learning happened because of a combination not just of these deep networks, that I think we're right next door to one of the most famous deployers of deep networks, but that we combined them with convolutional networks. In other words, there was a domain knowledge that was applied. We didn't just get an infinite data set and pour it into a DNN or an RNN and let it figure things out. We actually had to set up these convolutional layers in the network that approximated what we thought might be happening, say, in early visual cortex, for us to have some of the big breakthrough results that occurred against ImageNet in the last decade. It's this important domain knowledge that allows you to adapt machine learning in an explosive way to some new task. We've effectively built our own kind of convolutional networks, I won't go into the details here, that allow us to map neural activity directly into deep nets and use those as control networks for devices in the world. So, first thing I'm going to do is show you, this is actually me, and it's just me, and it's basically a hand, a virtual hand that we created that's mapped to my actual movements. Now, there's no camera there, it's not watching me, it's just paying attention to the nerve itself and recreating all the fine movements of my hand, the finger individuations, even some complicated things like the thumbs, and with really real-time resolution. What's amazing is I can do this in real time because the electrical signal actually precedes the movement. I think this is meant to emphasize that there's no camera here, so he's doing it behind his back. In some ways, very important here. Again, it's the nerve. My hand is moving because the nerve wants it to move, even though I can't move. Let's see what's up next. Here we're going to show you that we actually have models that allow us to read out the forces that you're generating across joints. So it's not just the posture, it's basically the level of effort in a posture, whether it's an open hand that you're stressing or the fist. These are all the different pinch forces you can generate. And these forces are actually a very convenient way of manipulating the world. This is how you do things today. It's how you move a mouse, it's how you control a joystick, etc. It's the force modulation, not just where your hands are positioned. So we have a philosophy that says that cameras are the wrong way to interact. I don't want to use a Kinect. I don't want to do a monkey dance. I don't want to dance like Tom Cruise to fly through a spreadsheet. I want to do very subtle movements that rely on the forces that I generate, which is the kind of thing that your brain is doing, not the kind, it is the thing your brain is doing all day long. Even as you sit there, modulating your posture, your brain is spending an enormous amount of activity making sure that your spinal muscles are finely balanced and creating co-contractions that keep you upright. This is the non-stop computation of movement that your brain is doing, and we want you to continue to have the joy of doing that, just like you do, as I said, when you're driving a car. It's such an easy task to do, and has very little cognitive load. So, let's see what this video is. Now I'm going to introduce you to neurocontrol. So here I have to go into a little bit of the biology, and I'm actually stunned at the number of neuroscientists who either never knew this or lost track of it. And it's really the key to how we're able to do our work. So you've got this spinal cord, and there's some set of neurons at a certain, say, cervical level here that control the hand. And this is a segment blown up here in the spinal cord. And you'll notice there's 3 different neurons. There are a red, a blue, and a purple. And they're connected into a muscle here. And that axon splits out, and it connects to different fibers in the muscle. That cluster of neurons together, what we call a motor pool, all talk to the same muscle. And any one neuron can only talk to fibers in a single muscle. But the most important part of this is that these fibers aggregated together, you have hundreds of thousands, if not millions, in a big muscle. These fibers receive input from a single neuron, only one. It's crazy. You're not born that way. When you're born, this is all overwired. It's a crazy nest of connections. And when we see a baby moving like this, we call it motor babbling. What they're trying to do is get a winner-take-all process called refinement to play out such that all that nest of axons retracts from the muscle, and you're left with this exquisite mapping such that individual neurons control a set of fibers. We call that set a motor unit. And that set, say those 3 red fibers, are assigned to that single neuron. And you have the ability to turn that neuron on and off and control just those fibers. Now, there's some more complicated things that go on during natural movement. We call it recruitment. And it's a very important thing that we had really the biggest breakthrough in the company on is the violation of the recruitment law. So what you'll notice here is that when this neuron fires, at the same time, there's neurotransmitter released downstream, or when the purple neuron fires, the purple fibers also fire. The point is that those fibers generate an action potential just like a neuron does. And it really is an action potential with that same quasi-digital shape. The same thing every time. So what we're able to do, actually I'm going to go back to that for a second. What we're able to do is recreate the activity of that motor neuron, not by listening to it directly, not by drilling into your spine and putting an electrode right next to it, but because there is a one-to-one correspondence between that set of fibers, the motor unit, and that motor neuron. We know every single time there's a little action potential from the muscle, that specific neuron also just fired. It's one-to-one, it's 100% predictable. For the other neuroscientists in the room, this is not a probabilistic synapse. It is 100% release probability. Action potential is 100% of the time. There's no other synapse in the central nervous system that works that way. From a signal processing point of view, that's great. Because what it means is this giant fiber generates a huge electrical signal that I can see outside the body. I no longer need to drill in to see that neuron. I can see it. And rather than seeing the crude smeared EMG that represents the aggregate activity of a bunch of neurons, instead, I'm able to actually sort out and separate, which I'm going to show you in a second, the activity of individual neurons. I'm going to skip this quickly. This is to tell you that, in a lot of ways, this is boring old technology. We've been doing EMG, recording the biopotentials on the surface of the body for over a century. Even way back in the early 60s, we knew you could train somebody to control a single neuron. Now, the interesting thing is with the device that I've got over there that we've built, we can now actually look, and what you'll notice here are these peaks are at different points. This is a continuous recording across a whole bunch of channels, but now this is a single channel of somebody moving very, very lightly. And what you'll notice is there's 3 neurons here that are superimposed, that red, green, and blue neuron here. We can separate those out. We can decompose the really complicated electrical signal into those individual pulses. We call it spike sorting. It's one of the most well-understood and most, effectively at this point, most refined techniques we have in experimental neuroscience. This idea of sorting out the aggregate signal into its individual constituent parts. We've done it, and we've done it non-invasively for the first time. Now, once we have that, again, I'm going to speak to the ML thinkers in the room, it's a really convenient marriage to take the spiking output, the zeros and ones of biological neurons, and feed those into a recurrent neural network. They're kind of speaking the same language. We take the zeros and ones of the biological neurons and allow them to be chewed on, if you will, by these computational neurons, and then allow those neurons to drive feedback, what we call adaptation, to the biological neurons through your sensory system, vision and audition. So let's look at some examples of this. So this is a game called Dino Rider. People know this, built into Chrome. And he's just showing he can move there. But then he's going to not move and control it using a single neuron that he trained just before this. And he can do this in any posture. He's got control of that single neuron. We actually know how to go discriminate between him. I love that picture. Doing this in an intentional way versus when he's moving like this and he doesn't want that thing to fire. It's actually kind of trivial for us to know when that neuron is firing in support of natural movement versus, oh, he's trying to control something now. I hope you also noticed the temporal fidelity there. That was about 100 milliseconds accurate. The last thing I want on this slide is what I really want you to take away, which is that neurocontrol is in some ways the final interface technology. Once you're at the level of controlling things with individual neurons, there's nothing lower than that. There's nothing sort of more atomic than that we know of that your brain can do. So the problem now is to go exploit that as fast and as far as we can. So I'm going to show you a sequence of videos that go through all the different applications that we've been building for it. First, I'm going to start with virtual reality in a really kind of fun virtual reality game that we built, playground, if you will. And the goal here was to say, I don't want you to move. I don't want you to do things as if a camera can see you. I want you to have kind of like Luke Skywalker powers. I want you to be able to control objects at a distance. I want you to have the Force. So this is a colleague who's controlling this beam, and he's doing these very, very light gestures to play around in this interesting playground. And you'll notice he's got multiple degrees of freedom. He's making a fist to pull the thing towards him. And again, it's not that he's making a fist to move it, it's how much fist changes the speed of it. And he's making a pinch, and he's got 6 degrees of freedom here between different pinches, and he can change the speed with which he's rotating that thing. So I'm no longer limited to that 2-dimensional mouse. I have, in this case, 8 degrees of freedom, all with continuous dynamic range. Whoop. Apologies if I'm standing in front of some of you here. I think this is probably repeating, so I'm going to go on to the next. We've been doing a lot of work with clinical researchers and folks in the robotics field, and in particular, we've been working with John Krakauer on what's called prehabilitation, and with Jens Bo Nielsen on some really, really intriguing work to help alleviate spasticity in those afflicted with cerebral palsy. Prehabilitation is cool, which is somebody who had a hand transplant. Johns Hopkins is one of the only places in the world that does this surgery, and the idea is that that virtual hand I showed you me playing with earlier, if you let somebody without a hand play with that virtual hand for a little while, whoa, that didn't work. Huh. Maybe you could rotate that video, because this is a pretty important video. Is there a chance? What I'm going to show you is somebody who's going to be doing that hand for the first time. This is the first time they've ever put the band on, and I think it's impactful enough that I want you to see it. No. There we go. Let me try it here. No. Do you want to go to the next one? It looks correct on the next slide, but it's... Yeah, all right. Everybody tilt your head to the left. What you're going to see here is somebody who's actually playing with this thing. You want to... Sorry. Can you get it to play now? I wouldn't pause here, except this is probably my single best video. You can just get this one to play as is. All right. Is it? No, it stopped. It's playing here, but not here. Okay, so apologies. This hand is moving. The person has just put on the band for the first time, and they're slowly getting how to figure out the hand. And what you're going to notice is this is Greg Wayne from DeepMind. He doesn't have a left hand, and he's never done this before. So he puts the band on, and we're actually able to let him figure out how to control this virtual hand using just his nerve. And he figures it out fast. He figures out how to use each individual finger. And then he's able to actually make grasps. He says in the video, if you can't hear him, he says, "I've never grabbed something before." Greg is a scientist at DeepMind, actually, that is a colleague of ours from Columbia. I find this to be extraordinary. He's able to do this grasp and read the force detection. He's able to output a force that he can't actually do, but he can do it neurologically. I'm going to go forward here. I'm going to skip the call-outs to these folks, but I'm going to show you some things. This is Adam Bernswey, one of our scientists, making the world's most expensive and extraordinary back scratch. Boy, we're having some video problems with all these. I think we should fix, because they're going to be, I think we're going to keep having problems on it. Any idea?
Let's give it a minute to do that. Should I come up and chat with you for a couple of minutes while it fixes?
Sure.
Yeah, let's do that. There's nothing like a bit of extemporizing. Is there really?
Oh, there you go.
Yeah, you must have had demos before that occasionally go awry.
Always.
Always. So one of my questions, am I on? So I suppose one of the first questions that we would you'd come out with here is we see the therapeutic uses for these applications. What do you imagine being the non-therapeutic uses, like the mainstream uses?
So I'm showing a couple of therapies in here, and I want to emphasize, we didn't start the company to really address what we call neuropathies or motor neuropathies, problems of the motor nervous system. We had a philosophy that if you build a technology for 8 billion people, you're going to solve a ton of problems for people who have motor neuropathies or some limb loss or other losses in their life. So we wanted to start going really, really broad. So you'll see a demo in a moment where I'm actually generating text on screen really quite rapidly and fluidly. But for people who've had significant motor loss, because we're at the level of neurocontrol of individual neurons, they don't have to move to be able to do this. Even somebody with ALS who has just a very, very small number of motor neurons that are still active, that's sufficient signal for us to go extract out and allow you to use that in a new kind of control paradigm. Or if, say, you have a problem of spasticity or, say, a resting tremor. Well, mechanically, a resting tremor is a bitch to deal with. But neurologically, it's kind of actually easy to deal with. It's a resting tremor. It's a very rhythmic signal. We just filter it out and allow that person with resting tremor to control a 2D cursor without any rhythm to it. It's really quite extraordinary. So our goal is to allow you to get that kind of facility for a person who's lost movement, but now for you to now have that ability to control things that you simply couldn't control before, i.e., rather than a 2D mouse, what's it like to have 2 3D mice at the same time? So if I'm in virtual reality, how do I move myself in 3 dimensions? And how do I simultaneously move an object at a distance in 3 dimensions? Cognitively, this isn't difficult.
But I have a follow-up. You said cognitively it's not different. It feels like sometimes I struggle to walk off a stage without falling off it. And now you're going to give me 2 3D mice. Can I achieve that?
So
we're going to give them another minute to try to sort this out. Yeah.
Who here has a cup of water in front of them right now? I just want to take on this question of how hard is it to do this. So if you do that, you take a sip of water right now and demonstrate it to everybody. That is the most complicated thing you have ever done. The degrees of freedom that were involved in that, the adaptive control, the ability to grab it and adjust for the weight of it and the fluid, and you've never done that task before in your entire life. Robots are famously terrible at these liquid-based transfer tasks. You, what we call skilled reach or skilled reach and grasp, you're really good at it. And you didn't have to sit there and focus on it. You just kind of did it. You have this phenomenal ability to control what are 27 degrees of freedom in the arm and to respond in real time to the load changes in the cup. You have all of the cognitive capacity to do this.
No, that is amazing. So we will be able to learn with those new tools. I suppose in the way that we have learned to use tools that our forefathers didn't have, like mice in the first place.
Sure. And I think it's, when we think about a keyboard, that's a 19th century technology that was deliberately created to slow us down. And yet we haven't really moved forward from it in 150 years. When you start thinking about a textual interface at the neural level, well, we ought to be able to exceed the performance of speech. which might be where our cognitive limit is in terms of speech production, or language production, I should say.
And I'm curious about this, the amazing thing that you started at the beginning where you showed how much comes in and yet how limited we are putting it out. And you've tacked this onto the neurons that come out and drive motor control. Is that the full extent of the space that we can explore cognitively, or are there still things that might be beyond
So,
that?
there's a reason we care about motor control, and that's because that's where your brain makes a decision. I don't want to extract information from you about all the things you don't want to do. But guess what? Your brain is thinking about all those things at the same time. Everything, things you just did 500 milliseconds ago or 5 seconds ago, and the 20 things you don't want to do are all active in cortex. There is no one place in cortex that is the ideation center, that is your true belief system. When you make a decision to do something, all of that neural information collapses down to motor output. That's where the decision is expressed. That's why we record from the motor nervous system, and not from this global cortical regions.
Does that say something about how we might build better AI systems? That having this sort of instantiation in the real world with motor feedback is a key part of the learning loop for building a sort of a real AI?
Yeah, that's a deep question. I was talking with the person I showed you there a moment ago, Greg Wayne from DeepMind, and we were talking about whether or not you can train a machine to learn language just by reading a lot and creating statistical models of language. And he said, no, what he really thinks needs to happen is you need to get it to read a lot and watch a lot of YouTube. And it's the YouTube part that's critical, because that's how you start to find out these things like spatial relationships that allow full expressivity in language. And you don't get that without some kind of either interior visualization or actually being able to witness it in real time. What I would say is we believe, again, you have a phenomenal input ability, you have a very limited output ability, that we don't need to create neural prosthetics that can enhance you in terms of your sensory system, that we need to actually just increase your output, and that your sensory system will adapt in real time to this kind of new rate of information flow. Now, what that says about AI, I would only say that we think systems learn faster when that full loop, the input and output loop, are more balanced.
Well, apparently the systems run by our tech team may well have worked in that time.
So we've
Thank
gone
you.
long here, but
let's
thanks.
see. Let's go for it.
Let's see if we can show at least a couple videos. This is the Greg Wayne video. I'm going to go by it. This is that video. I want you to see this. Whoops, sorry. This one is at Johns Hopkins. No. Here we go. And this is, they did this. It took them 5 minutes to hook this up, that same hand model. So at APL and Johns Hopkins, they do the most exotic, fully continuous robotic hands for people who've lost limbs. And they were able to actually do this the day we gave them a device. This is an old research device. And you can see he's doing full grasps. He's able to get full finger individuation. I want to come to what we think of as, this is really awesome. This was something we weren't predicting. It just sort of happened. So this is Alex Barachant again. And what's happening here is the machine is trying to predict who's wearing the band. And the reason this happens is because I said that thing about when you were a baby, you had all this motor babbling and it caused all the neurons to retract. What that means is that you have a neural signature which is unique to you. Not even your twin or your clone has that signature. Nobody in human history has that signature. It is the most exquisitely specific bioidentifier. So this is another colleague, actually from UCL, who's trying it on, and it says, hey, I don't know who you are. So it knew who Alex was. It doesn't know Spencer. And then my co-founder here, Patrick, will come in and put the band on. And really, in 800 milliseconds, it figures out who's actually wearing the band. It's a little bit longer. He puts it on. We'll plug it in. Sorry, this is slow. Same band, same everything. And as you'll notice, it's like, there you go. It's that specific. I think that's extraordinary. So now I'm going to show you some other things. This is Adam again, just typing. He's doing these little micro movements on the desk. This thing's kind of a QWERTY-ish model that has evolved because it's become adaptive, so he no longer has to do the full stride. It's real. He'll even make a mistake here. Hello world. This is the future. Universal control for 8 billion people. Here's another version of this. We were imagining what it would be like to be in AR. Here he's actually doing a whole browser experience, and he's going to like tag something on Insta, and then he's scrolling around using these little pinch forces. He's going to write a quick note to somebody. Oh, he's actually controlling the mouse simultaneously, so you're no longer reaching for a mouse, going away from the keyboard and back. It's all just sort of right there with little very, very fine movements. When he does that, he's unselecting things. He's going to scroll again. Goes back in the browser. I think he'll probably write a quick message to Tane. Getting this is all sort of in one context. It's one control system. This is real and live. This really does work. I don't even know what this next one is. Let's go find out. Oh, maybe we can end with this one. Can you turn up the sound? This is, I think, my co-founder playing asteroids without moving. This is a complicated game. There's 2 full continuous degrees of freedom, plus a bunch of discrete controls for him to actually fire, and he's able to do it just out of the motor nerve, and that's a neurocontrol example where it's just activating motor neurons, but it's below any threshold that causes the muscle to actually contract. And you can play relatively complicated games. What I love about that is Asteroids is a 2-handed game in the arcade, and he's able to do that without moving out of one hand and do it kind of casually, whether his hands in his pocket or on a table. There's other videos here. I'm going to skip them and leave you with this. I think that's obvious. Right, thank you. If we have time. Sure. Okay. If anybody has a question, I'd love to take a question or two. There's a chance.
If anyone has any questions, yeah, we'll get you a mic.
Great.
Start with the lady up here. Oh, gentleman. I can't see your hand.
There you go. There's a mic right here.
Thank you very much. Is it on? Yes. Thank you very much. My question is, do you see any ethical risks in this behavior? I'm a psychiatrist with a law degree from Toronto, and I'm interested in vulnerable populations, and I just wondered whether you saw any ethical risks in this development.
I'd like to, do you think it's specific to vulnerable populations or just a broad risk? Like any new technology, you try to create it and certainly we have, in a way that we think is people positive. I'm somebody who doesn't believe there's such a thing as values neutral technology. I think all technology has some bias for good or bad. I won't go into what things online that I think have a bias for bad, but I think this technology has a fundamental bias for good. It has a bias for good. It has a bias for empowerment. I do think it is fundamentally about increasing your control in the world and your feeling of control. Now, how does this get used in some misguided way? Obviously, it can be used to increase lethality in some militaristic context. Or, as I showed you, that ID is really kind of extraordinary. This thing knows you in 800 milliseconds. Well, that's a very positive thing in some contexts and a horrifically negative thing in another context. If you think about somebody using this as a low jack on your ankle to make sure that you're always available and always are who you say you are. That kind of identity tracking, again, in the big arc of history, is really important and empowering for people. But as we've learned, that kind of identity tracking can actually get perverted dramatically. I don't want to avoid any responsibility for this, other than to say I'm pretty committed to human positive outcomes here. But beyond that, I can only hope on my fellow humans that we exploit it in the right way. Sorry, another question. Anywhere. Sorry, over here.
When am I going to be able to buy that watch
Oh,
on
this
the
is
table?
this is real. This is live. If people, I've got a live demo machine over here. If people want to stay after, this is the wrist version of it rather than the arm version. It's live. See, the LEDs really work. It's the blue. It wants Bluetooth. It can't find the machine over there. So we started to sample this. This is called Control Kit. This is our first device. This is, I didn't really go into this much, but this is the surface electromyographic array that we read. It's a full array, so we get a full view of all the different activity that's coursing through the arm. We sent this out to about 30 different, mostly research labs currently, and we are having people sign up. I should probably put that on the last slide. If you go to control-labs.com is where we're asking developers and other curious folks to sign up for Control Kit. We are slowly ramping up through the first 500 devices right now, and we intend to bring this out to 50,000 people by the end of next year. But this year is really focused on developers who are committed to exploiting the signals. So it's not for consumers. It's not even remotely ready for consumer usage, but it is ready for people designing new kinds of digital experiences to allow you to break through the curse of the keyboard and mouse.
We have time for one more, I think.
Okay, last question, thanks. Maybe here. That was the most.
Said that at the moment we're up to about 100 bits per second in terms of output. What has that bit rate gone up to with your devices?
I wish I could tell you it's a lot higher right now, but it isn't yet. So I think Patrick is estimating somewhere around 400 bits per second right now when we did the 3D mouse simultaneous with typing. But we've really only gotten this to work in the last year. From my perspective, there's an important first principle reason why we ought to be able to get to kilobits and then megabits, but even kilobits would be extraordinary as an increase over what you have today. But the estimates, and then we did some Fitts law stuff, testing different accuracy measures that allowed us to say it's creeping up from there. The point is, it's not lower. All right, thanks so much for your time today. Thank you. I'll stay around afterwards.
Yeah, okay, perfect. So, please, if you go, thank you so much for that. Oh, I'm not talking to this, so I've forgotten what I'm doing. And thank you for staying behind. Reardon will be up at the front after we wrap, and maybe there'll be an opportunity to, for a few people at least, to see the device. Now, Tabitha, who runs this, has given me some very explicit instructions, so I'm just going to say this, read it out to you. My heart swells with how amazing you've all been. I have a plan for the closing, and it goes like this. You are going to ask people to wait so we can have a big CogX thank you and send off. So please wait, because they have all worked super hard, and we need to sort of thank some people. But I do want to just try to summarize the last 2 or 3 days. Was anyone here right at the beginning on Monday morning when it was pouring and we all wanted to go home and were freezing? Yeah, thank you for staying. You may remember that I said at the beginning that the primary thing that we need to understand is that the systems are changing and the rules are changing as a result of these types of technologies, and that is what history has told us. And what we wanted to do, Libby and I, over the last 2.5 days, is take us through the fundamentals of some of those key changing technologies, take us through the applications. But I did ask for you to remember this one question. As I see these technologies, as I see the pace with which they are moving, how do I think they are going to interface in the world in which I live? How will they force the rules to change? What will the second order effects to be? I'm not going to ask you to give me any of those answers to that question, but I would like you to take that away and to think about it. And there's one other thing I'd like to say. So one thing we didn't really talk much about over the last 2.5 days, and it was an oversight really on my part, so I'll bear that blame. I mean, today, Theresa May, who I think may still be Prime Minister, said that the UK would aim to be net zero on its carbon emissions by 2050, which is a really enormously small step. 2050 is far too late. I did have a speaker who was going to jump up and chat to us, but he got a virus. He couldn't make it. But his main point is that the scientific consensus is that we have 12 years. 12 years is 4,000 days. I started a countdown clock on Sunday. I said we've got 4,000 days to get to net zero, 4,000 days to figure this out, 4,000 days to keep CO2 limits below 450 ppm. So today is now Wednesday, so it's 3,997 days. It's not a lot of time. I made a mistake by not having any significant sections on climate change in the last 2.5 days. Please don't make that mistake yourselves in the small actions you can take over the next 3,997 days, in the actions you can take when you go back to your organizations, and the actions that you can take in expressing your political will. It is the most serious question that we face, and we should have spent more time in this stage talking about it. I'm sorry we didn't, but I do hope you still enjoyed the last 2.5 days. So, we have some slides. I also thank you. I also just really want to ask everyone here, please to stand up and thank our AV team and the support team and the runners. They have been on their feet in the rain for 2.5 days, and let's give them a big clap. Oh, and of course, and of course, as you might imagine, a lot of the really hard work and the creativity and the planning was done by my colleague Libby. And so please say thank you to Libby.
Thank you, Azeem. But I think I said at the beginning, that's really not true.
And finally, thank you to all of you, and hopefully we will see you next year.